Hi there, and welcome back if you joined us for the Python Introduction course. And if you skipped that course, and this is the first time we're meeting, well, welcome aboard. If you did join us for the introductory course, you've heard this before, and no doubt you're going to hear it again. When you work in IT, computer programming skills open up an incredible amount of opportunity. You've also heard us use the metaphor of the toolkit, that every successful career in IT is built upon a toolkit of skills, experience, knowledge, and curiosity. Python scripting is a powerful tool in your IT toolkit, and you're here because you've taken the first steps on your Python journey. By now, you're starting to understand programming concepts, and you've seen how an IT specialist might create automation to save time and cut down on mistakes. My name is Roger Martinez, and I'm a system administrator for hardware at Google. The team I work on maintains and monitors servers that Google hardware engineers use to design and test silicon chips that Google makes for their Pixel phones. I'm really excited to be your instructor for this course. As you know, this program has been developed and designed exclusively by Google. Each course takes place at a different campus location to bring you some extra Google goodness. And in case you're wondering, no, we aren't actually orbiting a distant galaxy. Although we are trying to bring you a universe of knowledge about Python. Don't worry, the curriculum is stronger than a lot of my jokes. Throughout this program, you're going to meet other Googlers besides me and the other instructors. Many of them started their careers in IT support just like me, learned programming, and advanced onto more technical roles. They're excited to share their stories with you about how they've built their IT careers through persistence and a commitment to learning new skills. Some of them will also share more detail on their jobs and what their day-to-day tasks look like. Before we dive into the course, I'd like to share with you a story to give you some insight into why I'm excited to be here teaching you this course. Years ago, when I started college in New Jersey, I really didn't know what I wanted to study. A friend of mine recommended that I check out the IT program. I've always liked working on computers, but I had no idea that a career in IT was even a possibility. From the moment I walked into that class, I felt so out of place. No one really looked like me, no one sounded like me, and no one seemed to come from a background similar to mine. I dropped the class the next day, and I never went back. In hindsight, I kind of regret that decision. If I would have stayed in that class, then maybe the next Latino person or other minority that walked in would have felt like they belonged. Diverse ideas, experiences, and backgrounds are crucial to IT, to any industry really. And diverse representation is so important to showing the next generation that they belong in a field and that they can thrive there. So that's why teaching this course is so meaningful to me. Maybe it will, in a small way, help more people walk through that door and never turn back. Okay, enough about me. Let's talk about the course. So, what's ahead? By the time you finish the last video of this course, you'll be able to manipulate files and processes on your computer's operating system. You'll also have learned about regular expressions, a very powerful tool for processing text files, and you'll know how to use the Linux command line. And this might feel like a stretch right now, but you'll also write a program that processes a bunch of errors in an actual log file and then generates a summary report. That's a super useful skill, and by the end of this course, you're going to know how to do it. We'll kick it off now by exploring how to execute Python locally and organize and use code across different Python files. We'll then learn how to read and write different types of files and use subprocesses and input streams. We'll also dive into bash scripting and regular expressions, both very powerful tools for anyone working with systems. We'll even touch on automatic testing, which allows us to automate how we check if our code is correct. To finish, we'll put all of this together using the tools that we've acquired to process data and generate automatic reports. We'll also explain how to set up your own developer environment in your machine. And we really recommend that you do this. You'll need to have administrator rights to install software, or you'll have to ask the administrator to install it for you. Setting up your developer environment is a key step in being able to write and deploy powerful automation tools. So we strongly advise that you do this and get comfortable with working with it. In this course, we'll use QuickLabs, which is an environment that allows you to test your code on a Linux virtual machine. This lets you experience real-world Linux scenarios where you will need to write code to solve problems. We'll use Linux for our examples and exercises in this course. Linux is an industry standard for running servers, which is why we chose it. At some points, though, we'll talk about how things are done on Windows or Mac OS to give you a broader picture. While we'll be using Linux a lot, you don't need to run Linux on your machine to follow along. what you do need to do is make sure you've got Python installed. You also need to know how to install additional Python modules. But don't worry, we'll walk through all that later on. You've already learned the building blocks of programming. In this course, we'll examine different tasks that you might come across in your day-to-day activities, and we'll learn how we can solve them through programming. One difference I bet you'll notice real quick if you joined us for the Introduction to Python course is that we'll use a lot more modules than before. Oh, and when I say modules here, I'm not talking about the parts of this course. In this context, I mean the Python modules that we can use to get extra functionality for our scripts. Please remember, there might be some complex topics and videos that may not 100% sink in the first time around. That is totally natural. Take your time. Rewatch the videos a couple of times if you need to. I promise you'll get the hang of it. Also, remember that you can use the discussion forums to connect with your fellow learners and ask any questions that you might have. We're about to go on a fun and fascinating journey together into the universe of Python. So, let's go. Welcome to the next chapter in your programming journey. In the first course of the program, we built a foundation in Python. You've done an amazing job getting to this point. Now, it's time to take the next step. We're going to build on that foundation to boost your programming toolkit with even more useful tools. Are you excited? Are you a little nervous? Don't worry about a thing. As always, we're here to guide you and help you build your confidence step by step. Are you ready? Let's do this. To really get the most out of this course, we strongly recommend that you have Python installed on your machine. Having Python at your fingertips like this lets you understand how to run Python programs, how to install additional Python modules, and how it all comes together. So, we'll devote some of the next videos to guiding you through setting up your environment. We'll then use your newly configured Python environment to run Python scripts locally, discover how to organize code into different files, and talk about what code editors are for and how to choose what tools to use. After you get set up and familiar with your environment, we'll dig deeper into some automation concepts. In the introductory course on Python, we talked a lot about automation. We saw some automation examples and spoke about many possibilities that come with learning to program. In this course, we'll keep expanding on that base. We'll learn how to decide whether to automate something or not, and what it takes to put automation into place. To put this into practice throughout the course, you'll be running Python scripts on a remote Linux machine using QuickLabs. This tool lets you experience real-world scenarios that simulate programming problems you'll likely have to tackle in an IT job. If at any point along the way you feel lost or confused, don't panic. You can watch the videos as many times as you need to let the concepts sink in. Plus, you can ask questions in the discussion forums, which is one of the best ways to find extra information and to connect with other learners. So, we've got a lot to cover. Let's get started. In this course, we'll interact with the operating system a lot. So before we deep dive into more complex concepts, let's do a quick rundown of what we mean when we talk about the operating system, or OS for short. The operating system is the software that manages everything that goes on in the computer. It reads, writes, and deletes files from the hard drive. It handles how the processes start, how they interact with each other, and how they eventually finish. It manages how memory gets allocated to different processes, how network packets are sent and received, and how each program can access the different hardware components. Basically, the OS is a total boss and doesn't mess around. There are actually two main parts to an operating system, the kernel and the user space. The kernel is the main core of an operating system. It talks directly to our hardware and manages our system's resources. As users, we don't interact with the kernel directly. Instead, we interact with the other part of the operating system called the user space. The user space is basically everything outside of the kernel. These are things that we interact with directly, like the system programs and user interface. So when we say operating system, we're referring to both the kernel and the user space. The operating system does a lot of things. It does so much that we need a bunch of courses to cover all of it. But for this course, we'll focus on managing files and processes on the OS running on your computer. The scripts we'll write will all run in the user space. In some cases, though, our scripts may interact with the kernel of the operating system to get extra information or to ask it to perform certain operations. As you probably already know, there's a lot of different operating systems out there. The major operating systems used in IT today are Windows, macOS, and Linux. The Windows operating system is developed by Microsoft and is widely used in the business and consumer space. Most PCs come with Windows as the default operating system. macOS is developed by Apple and is mainly used in the consumer space. If you purchase any Apple computer, it'll come with macOS preloaded. Linux is an open source operating system. Open source software is free to share, modify, and distribute. Score. Linux is used heavily in business infrastructure. Most servers in the world today are running Linux. It's also available in the consumer space, although less common. Linux itself is actually the name of the kernel originally developed by Linus Torvalds, also a total boss. Because of the evolution of the rest of the operating system, we typically use Linux to refer to both the kernel and the whole operating system. Today, Linux has grown into a huge community effort with developers all over the world contributing to its success. Because Linux is open source, a lot of different organizations package their own versions of it, unlike Windows or macOS, which are solely developed by their respective companies. We refer to these different flavors of Linux as distributions. Some common Linux distributions are Ubuntu, Debian, and Red Hat. If you've heard of Chrome OS, you may know that it's another operating system based on the Linux kernel. But unlike other distributions, Chrome OS is usually considered an OS in its own right. Lastly, the Android operating system, which is used a lot on smartphones, also runs a Linux kernel. You may have also heard of Unix. Unix is an operating system developed back in the 70s by Bell Labs. After its original release, the OS went through a bunch of different versions with different companies releasing variants of it. The fundamental ideas of how Linux works today are based on the Unix principles. And a lot of the tools that we use to interact with the operating system are open source versions of those originally developed for Unix. This is why these tools and operating principles are usually referred to as Unix, even though the OS we're using is called Linux. So Linus created Linux, which is based on Unix. It's basically a programming tongue twister. Try saying it 10 times fast. The macOS kernel and some of its user space are also based on a kernel and user space tools from the Unix family, known as BSD. So although the graphical interface is extremely different between the two, the command line is actually pretty similar. Like we said earlier, in this course, we'll use Python to interact with the operating system. Python is a cross-platform language. You can use it on Windows, macOS, Linux, and even lesser-known Unix variants like FreeBSD. It's even available on mobile phones. Since it's cross-platform, we can use the same Python code to get to our goal on any operating system, whether the goal is opening files, processing text, or managing running processes. This makes Python a great tool for IT specialists who need to interact with different operating systems. You can apply the skills that you learn from one platform to all the others. So how helpful is that? As we called out before, for the exercises in this course, we'll be practicing with Linux computers. We've chosen Linux because it's the industry standard when it comes to servers that are managed remotely and through automation. When it's relevant, we'll also talk about how the same concepts will apply to Windows or macOS. In my job as a sysadmin, I mainly work with the Linux operating system. I grew up using Windows computers and interacted with them through the graphical interface. The very first time I used Linux was when I was a teenager and my PC crashed. It wouldn't boot up into the user environment. I had a lot of different files and docs I didn't want to give up. So I did some research, and on a friend's computer, I burned a portable Linux OS called Slacks onto a CD. I got my PC to boot up from there and was able to rescue most of my files. Learning Linux opened up a whole new world of customization and configuration for me. When I first started, I found it really interesting, intriguing, and even a little bit scary. Today, Linux is the primary OS I use to work every day. We've learned a bunch of things about operating systems and their histories. If all those different names are making you feel like your human operating system is crashing, don't worry. You'll pick it up as we go along. Now that we know we're on the same page when we say OS, in the next video, we're going to get our computer ready to work with Python. They say that the best way to learn is to practice, 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 and then practice some more. So we encourage you to practice the exercises in this course by running the scripts on your computer. Doing this will help you hone your programming skills as much as possible and can spark new ideas of things that you could do through programming. As an IT specialist, it's important to know how to install and uninstall software in different operating systems. To run Python locally, you need to have it installed on your computer. We'll give you some pointers in the next videos on how to do this for Python, but we also encourage you to research how to manage your platform on your own. If you feel like you can use a refresher on how to do some basic operations in your OS, like installing packages or running commands, I recommend you take the course Operating Systems and You, Becoming a Power User. This course is taught by my colleague, Cindy, and can really help you get up to speed on OSs. You'll find a link to it in the next reading. As we said in the last video, you can use Python on all major operating systems. So it doesn't matter if you're running Windows, macOS, or Linux, you should be able to run Python locally on your computer. It may even already be installed with your system. To check whether you already have Python installed on your computer, open a terminal or command prompt and execute the Python command, passing -- version as a parameter. Depending on what's installed on your computer, there's a bunch of different things that can happen. It could say it doesn't recognize the command, which means you don't have Python installed. It could return a version that starts with the number 2, which tells us that you have it installed, but it's Python 2. Or it could return a version that starts with the number 3, which means, you guessed it, you have Python 3 installed. For this course, we'll be using Python 3. Some of the things we'll cover are the same on Python 2 and Python 3, but some can be pretty different. So make sure you have Python 3 installed. If running Python -- version returns a version starting with 2, try running Python 3 -- version. Your computer could tell you that the command isn't present, which means you'll have to install Python 3. Or it could return a version that starts with the number 3, which means you already have Python 3 installed. In the next few videos, we'll talk about how to install and set up Python on each operating system if it's not already there. After checking that you have Python 3 installed, we'll also learn about installing additional modules that aren't part of the Python standard library. You'll need these additional modules for some specific exercises in the course. What are these additional modules that we were talking about? In the Intro to Python course, we talked about the Python standard library. This comes as part of the Python installation and includes modules for the most common tasks you can do with Python. But there's tons of other things you might want to do in your scripts, and not all of them are in the standard library. This is where external modules come into play. We can use external modules for a bunch of tasks, like generating PDFs, serving web pages, creating compressed files, interacting with email, and a load of other things. So, how do we find what modules are available? When developers write a Python module that they think others might find useful, they publish it in PyPy, also known as the Python Package Index. We can browse this repository of Python modules to find the module we need. It includes thousands of projects which are classified by different categories, like topic, development status, and intended audience. These external modules are generally managed with a command line tool called pip. This is a cross-platform tool, so you can use it to install, update, and remove external modules on whichever operating system you're running on your computer. Next up, we're going to talk about installing main Python packages and installing external modules on Windows, macOS, and Linux. These videos are all optional. You can watch the ones most relevant to you. Or if you have Python already installed on your computer and you already know how to install external modules, feel free to skip ahead. Windows computers don't usually come with Python pre-installed. To check if your computer already has Python installed, run the command we talked about earlier, Python -- version. Nope, no Python here. Python isn't installed on this computer, so we'll need to install it. There are a bunch of ways to do this on Windows. We can download the installable package from the official website and install that one, get it from the store if we're using Windows 10, or we can use a package management system called Chocolatey to manage the installation. For this video, we're just going to install the package from the official website. But if you'd like to get a taste of Chocolatey, you can check it out and download it on your own, because who doesn't like things a little extra chocolatey, right? To find the installer, go to the official download page for Windows. On this page, we can download the executable installer for the Python 3 64-bit architecture. Most computers today are installed with 64-bit installations. So, if you don't know which one to pick, pick that one, unless you know for sure that your computer is running a 32-bit installation. Once the executable installer has downloaded, we want to run it. This will install a new software on our machine, so we need to run it as the administrator user. Before clicking Install Now, make sure you click on the Add Python 3.7 to Path box. The path variable instructs the operating system to look for executables in certain directories of our system when running commands from the terminal. We want to have that box selected so that Python interpreter gets executed when we invoke it from the command line. Great, it's installing. It might take a moment. Now that it's done, we can test to see if it worked. We do this by opening a new PowerShell and executing the same command as before. Nice! We now have an executable Python interpreter that we can use for testing the scripts that we write. As we called out, just because we've got Python 3 installed, it doesn't mean that we have the modules we might need for every possible script. Let's say we're tasked with writing some automation that extracts information out of a website. To get the contents of a website from Python, we can choose the request module, which is used for interacting with web services. First, let's check whether we have this module already available. Darn, the interpreter tells us that the module isn't available. Let's install it using pip. To do that, we'll call pip install requests from the command line, not the interpreter. Ah yeah, we've now got the module installed. Let's try to import it again from the interpreter. Awesome, it worked. And just to double check that, let's try to do something with this module. For example, we can use the get function to get the contents of a website. So the get function processed the website and the response object now has its contents. We can do a bunch of things with it. How about we check the length of the response text using the len function? Fantastic. Now that we have Python set up on our Windows environment, we are ready to have some fun with it. Feel free to explore on your own and try some things out. Up next, I'll show you how to install Python on macOS. You can check that one out, or you can skip ahead. It's up to you. By default, macOS ships with a version of Python installed, but it's Python 2, not Python 3. Let's check this out. So while we have Python installed on this computer, it's only Python 2. I wonder if we have Python 3 installed as a different command. Let's check. So we don't have Python 3 installed in this computer. Let's install it. There are two ways to install Python on macOS. We can either download the installable package from the official website and install that one, or we can use a package management system called Homebrew to manage the installation. For this video, we're going to install the package from the official website, but feel free to check out Homebrew on your own. To install Python on macOS, go to the official Python page at python.org. Now we'll click the Downloads menu. Because we're running this on a macOS computer, the website will automatically offer us a link to install Python 3 for macOS. We're now downloading the Python 3 executable installer for macOS. Once it's done downloading, we'll execute it, go through the license and terms of use pages, and finally install it. Depending on how your machine is set up, you might need to enter your password to perform the actual installation using administrator rights. Cool! Now we have an executable Python 3 interpreter that we can use for testing the scripts we're going to write. Let's check that it's working by executing the same command as before, python 3 -- version. Great. Now we have Python 3 installed. Like we said earlier, just because we have the interpreter installed, it doesn't mean we have all the modules we might need to execute every possible script. Let's say we need to write an automation script for handling event scheduling. To do that, we need to manage a bunch of different dates and due date operations, like calculating what date it will be in 2 weeks. To make our lives easier with all that date manipulation, we could use the arrow module, which makes it simple to handle lots of different dates. First, let's check whether we already have this module available. Misfire. The interpreter says there's no arrow module available. To get that module, we'll install it using pip3 command. Notice that on Windows, the command was called pip. On macOS, it's called pip3. So to install the arrow module, we'll call pip3 install arrow from the command line, not the interpreter. Now that we got the module installed, let's try again to import it from the interpreter. Nice! Looks like that worked. To check that we can use it, let's try to do something with this module. How about we use the get function in the module to create a date object from a string? Great. Arrow parsed a date from the string in the format we told it to use. And now the date object has that date. We can now operate with this object. For example, we can ask to increment it by 6 weeks using the shift method and then print it using the format method. The format method that we just used can receive a bunch of parameters. These parameters let us intuitively format the string that we print. We've got our macOS environment ready to go. Now we can use Python and start having some fun with it. Feel free to explore on your own and try some other things out. Up next, I'll show you how to install Python on Linux. You can check that one out, or you can skip ahead. It's up to you. If your computer runs Linux, chances are extremely high that your distribution comes with Python already installed. You can check to see this by opening a terminal and running a command like this. Okay, we have Python installed, but as we saw with macOS, it's Python 2. That's an old version of Python, and we want to use Python 3 instead. Let's check whether we have that. Nice! Python 3 is already there. In some Linux distributions, the Python command may already be using Python 3. In other distributions, like this one, you may need to use Python 3 as a command to access Python 3. In all of these courses, we'll be using Python 3, so make sure that you run the right command for your distribution. If for some reason your Linux installation doesn't have Python 3 installed, you'll need to have it installed using the package management system. The name of the tool to manage local packages will depend on the distribution that you're using. It's called apt on Debian, Ubuntu, and Linux Mint, yum on Red Hat or CentOS, and dnf on Fedora. If you're not sure what the right command is for your distribution, it's a good idea to do a little research to find out. We've included a pointer to more information in the next reading. While our computer here has Python 3 already installed, we still might not have all the modules needed to execute all the scripts that we'll write. So we still need to learn how to add these modules to our system to make the most out of our Python installation. In this example, we'll be using an Ubuntu computer and the apt tool to install Python packages. We'll talk about two different ways of installing packages. First, through the package management system, and second, through pip. As we said earlier, Linux distributions usually have a package management system, and it's a good idea to use it to install additional software on your computer. Distributions usually include separate packages for the different Python modules available. Say we're tasked with writing some automation software that resizes images to fit a specific size. We can accomplish this by using the Python imaging library, known as PIL module. This includes a ton of image manipulation functionality. To install this module on your Ubuntu computer, we can use the apt tool to install Python 3-pil package. One of the advantages of using the package management system to install packages is that we can set the system to automatically upgrade to newer versions. The package management system makes sure that any dependencies are also installed so that the module is ready to use. So let's check out this module that we just installed. The PIL module is very large because it includes tons of things that we can do for images. For this example, we want to open an image and check its size and format, so we've imported the image submodule inside the PIL module. Now, let's open a file in our home directory using the open method. Great, we've opened the image. Now we can check its size and its format attributes. Okay, the module's working properly. In this case, we wanted a module that was provided by the package management system, so it was easy to just install it using apt. In other cases, we may want to install module versions that are newer than the ones provided in the distribution, or that are not even present in the distribution at all. For cases like these, we can use the same command we mentioned for Windows and macOS, the pip command. For this scenario, we first need to make sure that we have Python 3 version of pip, which is called pip3 and is provided by the Python 3-pip package. We'll do this by installing the package through the package management system. This might take a minute. Now that we have pip3 installed, we can solve problems using a wide range of external modules. For example, imagine that you're tasked with creating an automation that processes the error log from our web service and then generates statistics on the amount of errors or when the most errors occur. To do this kind of data processing, we could use our cutest sounding module yet, Pandas, which is widely used in the data analysis field. All right, we have the Pandas module installed. Let's try it out with some sample numbers. Okay, we've imported the module. To state the obvious, since this is a tool for data analysis, we'll need some data to use it. Let's generate a few sample lists for the data associated with our website. How about a list of the amount of visitors we've had in the last 5 days? Let's add another list with the amount of errors generated during the same 5 days. Now that we have these two lists, we can use them to generate a data frame, which is the main structure used by the Pandas module to do data analysis. So we'll generate the data frame with the lists, adding the days of the week as indexes, like this. With this, we have a data frame that we can use for operations. For example, we can print it in a nicely formatted way. It's always fun to print stuff, but that's not really data analysis. The Pandas module allows us to operate on the numbers of each column. For example, we can calculate the mean or average value of one of the columns using the mean method. Nice! We now know how to install Python modules on Linux using either the package management system or pip. Are you ready to have some fun with it? Meet me over in the next video where we'll talk about interpreted and compiled languages. We've touched on how we can write a script in Python on a Windows computer and then run the same script on a Linux computer, or vice versa. This is the case for scripts written in many other interpreted languages too. So you might be wondering, what's an interpreted language? Well, when you want to run a program written in traditional programming language like C, the source code is fed into a piece of software called a compiler. The compiler translates this code into machine-level language, which means a language specific to the underlying architecture of the computer it's running on. The computer can read and execute the machine-level code directly. This makes compiled programs super fast to run, but the compilation process itself can take a bit of time. Some examples of commonly used compiled programming languages are C, C++, Go, and Rust. On the flip side, programs written in an interpreted language generally rely on an intermediary program called an interpreter. These programs use interpreters to execute the instructions specified in the code, rather than running them through a compiler first. So, this makes the development cycle for a program written in an interpreted language much faster, because the developer doesn't need to wait for the code to be compiled to execute it. And the same code can be read by interpreters running on different operating systems without needing to make any additional changes. The trade-off is that interpreted languages generally run slower than compiled ones. Python, Ruby, JavaScript, Bash, and PowerShell are all examples of interpreted programming languages. Last up, Java and C# are languages that use a mixed approach. The code needs to be compiled first, but it gets compiled into intermediate code. This means that instead of getting compiled into machine language that's specific for the current operating system, it gets compiled into portable code that can execute on different platforms. We execute this code using a program that's OS specific, the Java Virtual Machine for Java, and the Common Language Runtime for C#. Say, for example, you have a program that's written in C and you're running on Windows, but you want to run the program on a Linux server. To run the program on a different operating system than the one you're currently running on, you need to compile it on the destination OS. So, in our example, that would mean you would need to compile the source code in Linux OS, and preferably one that has the same versions of the installed libraries on the destination server. You could run the program source code in Python instead. If you did that, it wouldn't matter if you're running on Windows, Mac OS, or Linux. You could write and test the program locally and then just copy the script to the server and use it as is. The Python interpreter itself is a compiled executable that's platform specific. But once you have it installed, you can run your scripts everywhere. Okay, we've chatted a bunch about running Python scripts. Seriously, we've been talking a lot. I think it's about time we start doing, don't you? Hop on over to the next video where I'll walk you through creating and running a Python script. Okay, ready to see what our Python scripts can really do? We can run Python programs in several different ways. In this course, we'll focus on running scripts from a command prompt. And because our Quick Labs instructional environments will use Ubuntu, we'll concentrate on using a command prompt in a Linux-based setting. That said, with a little tweaking, the techniques we use here can be applied to other platforms like Windows or Mac OS. As we called out in our installation videos, the command to run the Python 3 interpreter might be Python or Python 3, depending on your platform. In our examples, we'll always show Python 3 because that's the command for the Ubuntu distribution we'll be using. You should use the right command for your platform. As we saw in our installation videos, when we run the Python 3 command, we get an interactive interpreter. When we run this command, it prints a bunch of things. First, we're told the version of Python interpreter we're running. Then, we get some extra information like which compiler was used to build it, and then some suggestions for commands that we can use to get more information. Using the interactive interpreter, we can do everything we learned in the introductory course on Python. Like say, printing hello 10 times because, Python's always down to have a convo. Hey Python. So this is fun and useful for experimentation and trying out new concepts, but unfortunately, we can't save any of our work. Once you close the interpreter by typing exit or pressing Ctrl-D on Linux and Mac OS, or Ctrl-Z on Windows, the code you wrote isn't even saved. Boo. To make our code more permanent, we can store it in files. Saved Python scripts usually end with a .py extension, such as helloworld.py. Let's have a look at our helloworld.py file using the cat command, which is a command that shows the contents of a file on Linux. To run a Python script saved on a Windows system, you can just type the name of your script and the operating system will recognize it's a Python executable from the file extension. On Linux and Mac OS, you can execute the script by calling the Python interpreter followed by the name of the file. So here, the Python 3 command, the same Python interpreter as before, reads the contents of helloworld.py and then tells the computer to execute the instructions in that file. But typing Python 3 each time you want to run your script can get really old really fast. So, pro tip, there's a way we can avoid this. We can add the extra line to our file called shebang, which tells the operating system what command we want to use to execute that script. Let's try this now. First, open the file in an editor. For this example, we're going to use Nano, which is one of the editors available on a Linux system. Now, we'll add our magic line at the beginning of the file. This line tells the OS that we want to run the script using Python 3. It looks like this. And that's it. We can now exit Nano by pressing Ctrl-X, then saying that we want to save the file, and then accepting the proposed name, which is the same name that the file had before. All right, our system now knows it should execute the file with the Python 3 interpreter. There's one more thing we need to do to run the script directly without having to call the interpreter every time. We need to make that file executable using the chmod command. Remember that this command lets us change the file permissions. A file's possible permissions are read, write, and execute. To run the file directly, we want our file to be executable. This is how we do it. Marking the script as executable means that we can now run the file by just prefixing it with a /. Because the script has been marked as executable and the path to the interpreter is specified on the first line, the operating system will run that interpreter and pass the name of the script to it. This means that running ./helloworld.py is equivalent to Python 3 helloworld.py. This approach works exactly the same for both Linux and Mac OS. Maybe you're wondering why we need to prefix the script with a / instead of just writing the name of the script. The reason for this is that the script isn't located in any of the directories listed in the path variable. This variable tells the operating system where to find programs to execute. The dot in the / expression represents the current directory. So we're basically telling the OS to find the script in the current directory and then execute it. So we just created our first executable Python script. How cool is that? Now it's your turn to do it. Take some time and experiment with running scripts locally on your machine. We went over a lot of info in this video that's super important to get down. If there's anything that doesn't quite click yet, watch this video again and practice the scripts a few times. After that, we've got something even more exciting coming up. We're going to create our own Python module. Okay, got Python installed on your computer? Check. Got it running locally? Check. Created your first executable script? Double check. You're doing great. Let's keep going. In programming, we often reuse code that we've written or someone else has written. This is called code reuse, and nearly all languages provide some way of doing it. We talked about code reusability back when we first looked at functions. Functions let us group code into logical blocks that can be executed at a later point and as many times as we need. But as our scripts get bigger and more complicated, we want to be able to reuse more than a single function. We might even want to reuse entire scripts in other programs that we write. Let's say that you created a script that emails a daily summary of tickets you completed to your manager. The script has two main jobs. First, it assembles a list of the tickets you've closed by interfacing with the company's issue tracking system. Second, it uses that list to create an email and then sends it off to your manager. In a separate project, let's say that you'd like to automatically parse a system log and search for an event inside of it. If the event is found in the log, you want to trigger an email to notify yourself. Can you spot the functional overlap in these two scripts? Both of these automation projects need to send an email message. The most straightforward way to do this is to duplicate the email sending code, copying it from one Python file to the other. On the whole, this seems pretty easy, but duplicating code in this way has some ugly downsides. First, every time you need to make a change to either script, you have to remember to do it to both places. That means you'd have to do any update and bug fixes twice. Ugh, no one wants to have to do that. And on top of this, if your coworkers want to use the same email code you wrote for their own projects, they'd probably have to go and create new copies. As you can imagine, keeping track of all the places it's being copied to quickly becomes tricky, and so does sharing different versions. So, instead of going crazy trying to maintain a bunch of different copies of the code, we can put the code we want to reuse into a separate module. This way, we can have our scripts and our colleagues' scripts import our code without having to create multiple copies. Great, but first, we need to create our own Python module by putting the contents that we want to be part of the module into a separate file. To use the module, we'll import it using the file name. We can access each function, class, and variable defined in the file by using dot notation. Let's see this in action. We have a file called areas.py, which contains functions to calculate the area of different geometrical figures. We can see the contents of that file using cat command. We have three functions defined in this module. The circle function uses the math.py constant. That's why we import the math module at the top so that we can use it. Okay, we've seen that the functions are defined in the areas.py file. To use them in an interpreter or a script, we can import the module by typing import areas. Let's do this. Perfect. We've now loaded the areas module and can use it to calculate areas. Let's calculate the area of a triangle and a circle to test this out. Our areas module is pretty small and simple, so it fits nicely in just one file. In some cases, the code we're working with can become more complex. and it might make sense to split it into submodules. In this case, we'd create a directory with the name of the module and separate .py files for each of the submodules. To see what we mean, let's look at a list of files shipped by a module installed on this computer. The request module using the ls-l command. Ugh, this module is super complex, so all the things it does are split into separate files. Notice the init.py file. This is a special file. It's read when the module gets imported, and it's used by the interpreter to check if a directory with Python files should be a module. So, if you have a module that's split into separate files and you want the interpreter to recognize the directory as a module, you'll need to create the init.py file. Even if you don't have anything to put in this file, you need to create it. You can leave it empty, but it needs to exist for the interpreter to recognize the directory as a Python module. Wow, that was a lot of stuff to grasp. But now we know how to create our own executable files and modules. It's a little complex, so don't worry if you feel a little shaky on it right now. We'll keep practicing these concepts until you can do them in your sleep. When you start writing your own scripts, you eventually come across these websites that mention IDEs. This term stands for Integrated Development Environment, and usually refers to a code editor with some handy extra capabilities that make writing scripts a lot easier. We do most of our programming work in code editors and IDEs, so it's important to find one where you feel most comfortable and productive. It's a good idea to invest some time now in getting to know a few editors and IDEs to find the one that you like best. There's a bunch of different editors out there. Some have only a few additional features while others have a lot. One of the most basic extra features in code editors is called syntax highlighting. This means that the editor recognizes the language we're writing our code in and highlights the pieces of code that make up the syntax of the language. Let's take a look at this in a text editor called Vim, which is available on Linux. Vim includes syntax highlighting. So if we open the areas.py file that we showed earlier inside Vim, we'll see that the code includes colors highlighting the syntax. We can see that reserved keywords like def or return are shown in one color, while the names of the function are in a different color, and even numbers are in another one. To exit Vim, type :Q. Another common feature offered by code editors is called code completion. Let's check out the use of this feature with a different editor called Atom. Here we have our areas module open in Atom. We see that it also uses syntax highlighting. The colors are different, but the idea is the same. Now let's write a new function called donut, which will calculate the area of a 2D donut as the difference between two circles. Donuts. When I type def, the editor tells me that this is a keyword to write a new function. After typing the name of the function, I write the opening parentheses, and the editor knows that there will be a closing parentheses, so it writes it for me. After defining the function, when I press enter, the editor knows that the code needs to be indented to the right, so it automatically positions the cursor right there. Pretty helpful, right? Now, when I type ret, the editor suggests that I may want to type return. It's like it's reading my mind. By pressing tab, I accept the suggestion, and so my ret gets completed to return. Nice. Let's save with Ctrl+S and close our program with Ctrl+Q. And that's the power of code completion. When you need to write a lot of code, having an editor automatically complete the names of the variables and functions can save you a load of time. How you write source code depends on your personal taste, your preferences, and the applications available for your platform. You can go with whatever is already installed on your computer like Notepad, Text Editor on Windows, TextEdit on macOS, or Nano on Linux. You can choose a more advanced code editor like Atom, Notepad++, or Sublime Text, or go for a fully featured graphical IDE like Eclipse or PyCharm. Once you've found your favorite one, it's a good idea to take the time to familiarize yourself with the editor's capabilities so that you can get the most out of it. Feel free to experiment writing some scripts and executing them until you feel comfortable editing your Python scripts. Now, a word of caution. As an IT specialist, you don't want to be completely tied to just one editor. It's possible you may need to debug a problem on a computer with a different editor installed, and you don't want to waste time installing your preferred editor. So, make sure you have a basic idea of how to use an editor that's installed by default on the computers you work with. Graphical code editors with additional capabilities like Atom or Eclipse are pretty nifty and can save us a lot of time. But you should also learn your way around at least one command line editor like Vim, Emacs, or Nano for the times you might not be able to use the graphical editor. For example, you might need to connect to a remote server that's running on the cloud, where you won't be able to use a graphical editor. We've talked a lot about setting up your environment, and you can now write and run your own Python scripts and Python modules. Up next, we have a supplemental reading with more info, and then a quiz to double check that you're getting the hang of all these new concepts. In the Introduction to Python course, we talked about the benefits of automation for a bunch of activities, like doing repetitive tasks, analyzing text, generating reports, and a lot more. In this course, we'll build on these concepts by applying automation to more and more tasks. As an IT specialist, thoughtfully applied automation can play an important role in your work. Look at automation like an IT force multiplier, a tool that can increase the effectiveness of an IT team without needing to increase the number of team members. In other words, automation can allow the IT infrastructure to scale, keeping pace with growth and demand. Scalability means that when more work is added to a system, the system can do whatever it needs to complete the work. For example, think about the impact on IT when a company hires a new employee. New employees might have to access a range of technology resources to do their job. Onboarding tasks can include creating a user account, a mailbox, and a home folder, and setting up the appropriate permissions to control access to various systems and resources. If the company doesn't hire a lot of employees over a given period, someone could manually do these tasks each time a new person is brought on board. Although I'm willing to bet that that will get tedious real fast. But as the number of new employees increases, so does the time it takes to set them all up in the system. If a company hires 10 times its usual number of new employees in a week, the IT person in charge may find themselves performing nothing but the new employee account setup and going crazy at the same time. They would probably have to put a bunch of other projects on hold until they've set up all the accounts. As a human, they may also make some mistakes during the provisioning process, like misspelling a name, forgetting a step, or giving a user account the wrong permissions. They then have to fix these mistakes, which means even more work. Yikes. Now, imagine if the company continues to hire at this pace. They might need to assign another IT specialist to pick up the work that's being neglected because of all the new accounts to set up. Or there might be so much to do that 2 IT specialists might need to be assigned to the account setup. Basically, this doesn't scale well in terms of financial resources, mental investment, or reliability, especially if the company continues to grow. What happens if the rate of new hires doubles, triples, or grows even larger? Throwing more people at the problem quickly becomes impractical. Okay, so assuming that we're all on the same page about how manual onboarding has its issues, let's think about how we can improve the process with automation. Well, instead of having one person interact with each separate system to create a new user account, a mailbox, a shared folder, and permissions, it'd be more efficient if the IT specialist could write a script to do all of this. We could then have a computer do these tasks each time a new employee is hired. When given initial information, like the new employee's name and job function, this script could carry out each step automatically, so humans would only need to intervene if a task failed for some reason. The computer would execute each step in the script and in the given order, and in exactly the same way. It would never need to deviate from these instructions. We could even improve the script further. Instead of having the IT specialist enter a new employee's information into the script each time it's run, the script could just read the data from a company's human resources system. That will make the entire workflow begin automatically on the employee's start date. In this example of automation, we've made a repetitive, time-consuming task faster and more reliable. We've also freed up human resources, allowing IT specialists to focus on more strategic or creative work. Another subtle but super helpful benefit of automation is centralizing mistakes, which means if you find an error in a script, you can fix the error once and for all, which isn't the case for mistakes made by humans, of course. Hopefully, you're now even more sold on the benefits of automation than you already were. But, as we've said before, automation is not a fix-all. If badly executed, automation can cause as many problems as it can solve. To avoid that, we need to know how it can go wrong. So next, let's check out some ways automation can fail. Hands down, automation makes our lives a lot easier. But despite its many benefits, when automation is implemented without thoughtful design, it can cause some serious problems. Let's take a look at some ways that automation can fail and what we can do to avoid them. Any task or process we automate comes with a trade-off. Is the time and the effort it'll take to write the script worth the potential automation benefits? A simple heuristic that can help us decide is to estimate how long it takes us to do a certain task and then multiply that by how many times we perform that task in a given time window. If we estimate that it would take less time to automate the task than it would to do it manually, chances are it's a good candidate for automation. So, if the time to write the automation is less than the time to perform the task, multiplied by the amount of times you do it, then automate the task. Let's check out a real-world example. Say you generate a daily report on your system's usage, and it takes you 5 minutes a day to do it. If automating this task takes you 1 hour, then in 12 days, you've already saved the 60 minutes it took you to create the automation. This would be a great use of your time, as it would free up those 5 minutes every day to do something else. If instead it takes you 10 hours to create the automation, then it would require 120 days or 24 working weeks to start saving time on the task. That's almost 6 months until you'd start reaping the benefits of your automation. It's even possible that by then, the requirements for the report will have changed, needing even more of your time. Usually, the decision of whether to automate or not isn't so straightforward. If a task is complex and performed infrequently, it may seem like automating is more trouble than it's worth. But keep in mind that once a task is wrapped in automation, anyone can do it. It can be very useful to automate a complex, error-prone task if it's critical that the task be done correctly, even if it's not executed that often. There are no hard and fast rules on when to automate, but the cost-time trade-off can help guide your decisions. A concept called the Pareto principle can also be a useful guideline to help you decide which tasks to automate. When applied to automation in IT, the Pareto principle states that 20% of the system administration tasks that you perform are responsible for 80% of your work. If you can identify and automate those 20% of your tasks, you could save yourself a whole lot of time. It's tricky knowing when it's best to automate, and automation that's been implemented can be fragile. If underlying systems change and the automation isn't updated accordingly, workflows can break. Imagine an automated backup system that periodically saves the contents of a sales database. Let's say the automatic backup program uses a disk identifier like dev SDA1 to know where the data to be saved is stored. What happens if a new disk is added to the server and the disk identifier changes to dev SDB1? The automation will no longer be able to access the disk it thinks it should be backing up, and it will fail. This process of software falling out of step with the environment is sometimes called bit rot. The actual bits in the script don't really decay, it's the assumptions about the implicit signals the script relies on that rot. It's important to think about how your automation will handle errors. Automated systems perform actions without human intervention, so it's easy to set and forget them. If an automated system fails and it goes unnoticed, the consequences can be really bad. Let's revisit our backup example. Imagine that the backups fail because the disk identifier has changed and no one notices. Sometime later, the sales database server crashes and the data needs to be restored. The IT specialist will be in for a nasty surprise when they discover that the automated system hasn't backed up in a while. False confidence in an automated system may also factor into decision making. For example, if the database needs to be upgraded, system administrators may be more willing to proceed with a potentially risky operation, since they believe they can recover the data from backups. So, how can we avoid these silent failures? You can build a method of notification into your automated systems. This way, if the automation fails, a human is notified and can investigate. This notification method could be an email, a new entry in the internal issue tracker, an update to a dashboard, or even a page to the person who's on call for the service. Whichever the method, it's important that the notification services the error so that a person can fix the automation. Worse than automation failure, though, is when automation succeeds but performs the wrong action. To build on our earlier example, what if the backup system was correctly performing its task but was configured to back up the wrong data? A restore of the incorrect sales data could lead to data loss or even data corruption, where customers might get charged the incorrect amount or billed for products they haven't even purchased. Oops. Sometimes a task completes, but it completes incorrectly. For this more subtle class of failures, we can use periodic tests to check in on the behavior of your automated systems. In our backup system example, we could schedule a regular restore of data from the sales database, and then check that the restored data is what you expected would be backed up. This testing process could be automated too, with scripts written to schedule the restore and to compare the data against some master dataset. Again, if any part of the restore process fails, the automated system could halt to prevent further data corruption and send a notification to a human who could investigate the problem. Along with flagging problems, good automation will make debugging easier by logging the actions it takes. The system log can be an extremely useful source of information when you're investigating an issue. We say that it's of forensic value. Our scripts can also be configured to write to the system log. Doing this creates an audit trail of useful troubleshooting information, which can help with the debugging process. Automation is an incredibly powerful tool that saves time, reduces mistakes, and facilitates growth and scalability. But we need to apply it thoughtfully to avoid some of the pitfalls that can arise from its use. Keep these things in mind, and automation can be a valuable asset in your toolbox. So, we've talked about the benefits of automation and the things we need to be prepared for. Let's now look at an example of something we can automate using Python. Say, for example, that you wanted to check the health of your computer. This can call for a lot of different checks. Verifying that there's enough disk space, that the processor isn't overloaded, that it has the latest security updates, and that it's running the services it's supposed to. To verify all of this, we need to know how to check each of these values. And of course, we'll do it by using some of the handy modules available to us. For example, we can use the shutil module and the disk usage function to check the current available disk space. Let's try it out in the interpreter. We'll start by importing the shutil module. Then, get the disk usage. Let's print the variable and see what's in it. Cool, so we get the total number of bytes on the disk, the amount that's used, and the amount that's free. We can calculate the percentage of free disk space by dividing the number of bytes free by the total and multiplying that by 100. Alright, but what about CPU usage? For this, we can use another module called psutil. This includes a CPU percent function that returns a number showing how much of the CPU is being used. The amount of CPU used at each instant can change a lot, since processes are starting and finishing all the time. So, this function receives an interval of seconds and returns an average percentage of usage in that interval. Let's try it out. We'll start by importing the psutil module. Then, call the CPU percent function with 0.1 seconds. When we're using the interactive interpreter, we can use the arrows in our keyboard to get back the lines that we wrote before. So, using the up arrow, let's execute the same line a few times. As you can see, this can vary a lot. Let's try it with 0.5 seconds. See how it's taking longer to finish than previous calls, but the numbers are more similar to each other? That's because the function needs to wait for the given time to calculate the average. Okay, so we've done a bunch of research. Now we can write our health checking script. We'll kick off with a script that'll do 2 health checks. First, we'll set our script to use the Python interpreter with the shebang. We know that we'll use shutil and psutil, so let's import those 2 modules. Let's first define a check disk usage function that will receive a disk to check and return true if there's more than 20% free, or false if it's less. And now let's write another function called check CPU usage. In this case, we'll check the usage for a whole second. We'll say the machine is healthy if the CPU usage is less than 75%. Great, we have our 2 functions. Let's now add the main body of our script where we'll check if either of those 2 functions returns false. So here, we're just printing a message that the user will see. We'll improve on the script later on once we've learned better ways of notifying our system administrators. We're almost done. Let's save our script, make it executable, and run it. So there you have it. Everything's okay, which seems like a great point to wrap up this exercise. All along this course, we'll explore practical automation examples which you'll be able to apply in your job. And as we talk about the additional functionality available, we'll be able to extend our automation knowledge to more and more areas. So how are you feeling? Some of this stuff is a little tricky, and learning about automation calls for a little bit of manual work. The irony isn't lost on us. So roll up your sleeves and practice these scripts on your computer. Also, feel free to rewind and rewatch if you felt a little lost anywhere. Whether you need to do a little review or you're about to jump straight into the next practice quiz, you're doing great. Keep at it. For the graded assessments in this course, we'll use the QuickLabs online learning platform. Before we dive into our first lab, let's learn a little bit more about QuickLabs. QuickLabs is an online learning environment that takes you through live, real-world scenarios you might come across as an IT specialist. QuickLabs works with the Google Cloud Console to spin up and create virtual machines. As a reminder, a virtual machine, or VM for short, is a computer simulated through software. This software simulates all the necessary hardware to the operating system that's running inside the machine. For some simulated hardware, the VM will use a portion of the underlying hardware for the simulation. For example, you can run 8 different virtual machines on a single laptop, or even more, each with a portion of the disk space, memory, and CPU time. In other cases, it will simulate the hardware by talking to the operating system running on the physical machine. For example, a VM will use an emulated network card to communicate with the outside world. The networking packets going through that emulated card will be transmitted between the software that runs the VM and the operating system of the physical machine, which will then transmit the packets over the physical network. Virtual machines have become a staple in a lot of IT departments, since they allow us to create new virtual computers on demand. We can also reclaim the resources they use when they're no longer needed. If, for example, you want to use software that's only available on one specific OS, it's easier to create a new virtual machine, use the software, and then delete the virtual machine once you're done. Looking back, I wish I had VMs to play around with when I was first learning Python. I mostly learned from books and online videos. To practice, I'd find sample math problems and try to solve them by writing code. It was nearly impossible to simulate real-world applications, like finding ways to practice how to write automation scripts without having a bunch of servers. It would have been so cool if I had virtual machines to practice with. Enter QuickLabs. These virtual machines run in the cloud, so you can have access to them over the internet wherever you are. Remember that when we say that a service is running in the cloud, we mean it's running in a data center or on a remote server. Each lab has a pre-configured list of actions that need to happen during setup. This includes spinning up a VM with a specific CPU and memory configuration and installing the VM with a specific operating system. The lab will also configure any other cloud resources needed for the exercise. This could include additional virtual disk for the virtual machine, or maybe a second machine. During the lab, you can access instances of QuickLabs created for you by using SSH, which is a command that allows you to interact with remote Linux computers. You can operate with the VM in the same way you'd use a physical machine running Linux. Once the lab is finished, QuickLabs destroys its virtual machine. This way, any CPU, memory, and storage that the VM used is returned to the provider's pool of available resources. It can also be used by other virtual machines doing other work. After this video, we'll give you detailed instructions on how to access and complete the labs. You'll use the QuickLabs for this and other courses in the program, so it's a good idea to spend some time learning your way around it. QuickLabs is a powerful tool that we'll use in this course and throughout the rest of the program. With QuickLabs, you'll get to experience solving real-world tasks through scripting. Of course, you'll need to know how QuickLabs works, but it's just as important to remember why we've chosen this tool. It will let you continue building confidence as you progress through your Python scripting journey. In the next video and in the next reading, we'll give you more info on how to log into QuickLabs to tackle the assessments in this course. You can always go back to them if you ever need help. Congrats! You finished the first module of the course, and you made it through the first graded assessment, just like I knew you would. We've covered a lot of ground in the past videos, so take a moment to congratulate yourself. Seriously, you should feel really good about this. Not everyone sticks with it like you have. Let's quickly recap what you've learned. We've talked about some new concepts and some you were probably already a bit familiar with. We talked about what operating systems are and why they're relevant to the world of IT. We went through how to install Python on your machine, how to run Python scripts, how to create our own modules, and how to set up your developer environment by choosing a code editor. We also learned more about automation, including its benefits and its potential downsides, and checked out some examples of when it's a good idea to use automation. We looked through the practical automation example that will keep expanding as we get further into the course. And last but not least, you did your first QuickLabs exercise, of course, where you put all this new knowledge to practice. You fixed a problem in a Python script, making it run correctly, and you also wrote and used your own Python module. That's amazing. Great job. Take a moment to give yourself a pat on the back. Your hard work is seriously paying off. Time to take a little break if you need it, and come back refreshed for the next topic. In the next module, we'll be talking about managing files with Python. I'll see you there. Welcome back. Let's take a quick moment to think back on what you've already accomplished in this course. In the previous module, you discovered how to install Python and set up your own programming environment. Then, you learned how to write and execute Python scripts locally. We then discussed when to consider automating and what problems we might encounter when doing that. And to finish up, you were introduced to QuickLabs, the platform that will help you keep growing your skills throughout this course. Wow, you should be impressed with yourself, and I hope you're as excited as I am for what's coming up next. Over the next few videos, we'll check out some ways you can use Python to interact with file systems. As an IT specialist, it's likely that you'll need to manipulate files and directories on a computer a lot. And when you need to work on a large number of files and directories, that's when automation can be a huge help. As a sysadmin, in my job, I interact with files and directories all the time. Sometimes, even if I have no intention of modifying them. For example, I use Python to check if a certain file exists on a file system before doing any other operations. As you might remember, operating systems like macOS, Windows, and Linux use file systems to organize and control how data is stored and accessed. Data is usually stored on a disk and saved in files, which are held in containers called directories or folders. File systems are usually organized in a tree structure, with directories and files nested under their parents. We know where a resource, like a directory or a file, is located within that tree structure by its path. An absolute path is a full path to the resource in the file system. For example, on a Windows computer, the absolute path to the folder for the user Jordan would be c/users/Jordan. On a Linux computer, the absolute path to the equivalent directory would be /home/Jordan. We call it absolute path because it doesn't matter where in the file system our script is running, the absolute path will always lead us to the resource. On the flip side, relative paths use only a portion of the path to show where the resource is located in relation to the current working directory. Relative paths are kind of a shortcut that you can use so you don't have to write out the full file path. But keep in mind, they only make sense relative to the current location. So, for example, if we list the contents of the directory examples, we'll get different outputs depending on what the current directory is. If our current directory is /home/Jordan, we'll get the contents of /home/Jordan/examples. But if the current directory is /user/share/doc/python3, we'll get the contents of /user/share/doc/python3/examples. In the upcoming videos, we'll do a rundown of the many things that we can do with Python to manipulate files and directories. We'll also look at a specific file format called CSV that we'll use to read and write data. So, we've got lots of good stuff ahead. Let's get to it. In the introductory course to Python, we provided information to our scripts by creating variables and passing parameters to our functions with the values that we wanted. This works fine for small scripts, but it's usually not ideal for larger jobs. When processing large chunks of data, it's a good idea to read that data from files. In programming, we work with files all the time. It's such a useful task that most programming languages have the ability to work with files baked into their core set of features. Python's no exception. It gives us file objects, which we can use to read and write to files. To open a file on our computer called spider.txt, we can write this code. What we're doing here is creating a new file object and assigning it to a variable called file. The parameter we've passed to the open function is the name of the file we want to open. In this case, we're assuming the file we want to read is in the same directory as the script we're running, but we can just as easily pass an absolute path to open a file in a different directory. When we open a file, like we're doing in this example, the operating system checks that we have permissions to access that file, and then gives our code a file descriptor. This is a token generated by the OS that allows programs to do more operations with the file. In Python, this file descriptor is stored as an attribute of the files object. The file object gives us a bunch of methods that we can use to operate with the file. Now, with this file object, we can read the contents of the file and print them to the screen. Here we've used the readLine method. It lets us read a single line of the file. Let's call it again, see what happens. Nice. This time we got the second line of the file. So how does this work? Well, each time we call the readLine method, the file object updates the current position in the file, so it keeps moving forward. We can also call the read method, which reads from the current position until the end of the file, instead of just one line. And washed the spider out. Out came the sun and... What? Wait, don't go. What, you don't like my singing? That's okay. Let's check out the other example. The file here has 6 lines in total. We read the first 2 with our calls to read line, and then the other 4 all together with the call to read. Just like read line, the read method starts reading from wherever we currently are in the file. But instead of just one line, it reads all the way through to the file's end. Finally, we'll close the file using the close method. This open, use, close pattern is a typical way of working with files in most programming languages. It's a good idea to close files after you've opened them for a few reasons. First, when a file is open in your script, your file system usually locks it down, and so no other programs or scripts can use it until you're finished. Second, there's a limited number of file descriptors that you can create before your file system runs out of them. Although this number might be high, it's possible to open a lot of files and deplete your file system resources. This could happen if we're opening files in a loop, for example. Third, leaving open files hanging around can lead to race conditions, which occur when multiple processes try to modify and read from one resource at the same time, and can cause all sorts of unexpected behavior. No one wins in a race condition. Now, I'm going to let you in on a little secret. I'm the worst at remembering to close my files. And you might agree with me, it could get pretty hard to keep track of what files you've opened and then to remember to close them. Fortunately, the creators of Python agree. So, to help us remember to close a file after we're done using it, Python lets us create a block of code by using the keyword with. Let's see what that looks like. As you can see, the with keyword lets us create a block of code with the work we want to do with the file inside of it. In this case, we want to take a line of data from the file and print it to the screen, which is what print file read line does. When we use a with block, Python will automatically close the file, so we don't need to remember to do that ourselves. Phew. One less thing to think about. Thanks, Python. Both the open, use, close approach and the with approach have their advantages. Using a with block is a good way to open and work on a single file, then have the file automatically close at the end of the block. On the flip side, using open outside of a block means we can use the file object in other places in our code, so we're not restricted to just one single block. But when taking this approach, we need to remember to close it when we're finished. Okay, I hope this helps you feel pretty comfortable with how to open, read, and display a file. In the next video, we're going to check out some ways of iterating through the contents of the file. We just took a look at the read line and read methods, which allow us to read a single line of the file or the whole contents of the file right to the end. Along with this, file objects can be iterated in the same way as other Python sequences, like list or strings. This is really useful when you want to process a file line by line. Say, for example, you want to make a whole line uppercase before printing it. You can do that with something like this. Cool. It looks like that worked. But what are these weird empty lines between the contents? Any idea what's going on? What's happening is that the file has a new line character at the end of each line. So, when Python reads the file line by line, the line variable will always have a new line character at the end. In other words, the new line character is not removed when calling read line. And when we ask Python to print the line the print function adds another new line character, creating an empty line. What can we do to avoid getting the empty lines? We can use the string method strip to remove all surrounding white space, including tabs and new lines, like this. Awesome! Now that we use strip to remove the new line character, we get the output without empty lines, just like we wanted. Another way we can work with the contents of a file is to read the file lines into a list. Then we can do something with the list like sort the contents. To do that, we open the file and use the read lines method. Let's see how that looks. First, we open the file. Then read all the lines. And now we close the file. Even though the file object is now closed, the lines variable has the list of lines in the file, so we can operate on it. For example, let's sort it and print it. There are two things to check out in this code. First, the lines have been sorted alphabetically, so they're no longer in the order that they were in the file. And second, we can see that Python displays the new line character using \n symbol when printing the list of strings. This is a way of explicitly showing that there's a new line character in those strings. In general, to display a character that's not printable, Python uses escape sequences with \, like \n. Another common escape sequence is \t for tab. And we can also use it for escaping quotes if we have a string that contains either a single or double quote. A quick word of caution. Methods like read or read lines that read the whole file at once are useful, but we should be careful when reading the entire contents of a file into a variable of our programs. If the file is super large, it can take a lot of our computer's memory to hold it, which can lead to poor performance. If a file is just a few kilobytes, like in our example here, it's fine to read it and process it completely in memory. But for large files, like a big log file with hundreds and hundreds of megabytes of data, it's more efficient to process it line by line. How's this all sounding? Let's do a quick recap. We've just learned how to open files using the open function and how to read those files using methods like read and read lines. We also learned how to iterate through a file line by line using the read line function and for loops. Up next, we're going to learn how to write content to files. Now that we know how to read files in Python, the syntax for writing to them probably won't seem too strange. Check this out. So, what do we have here? You can see that we're using the with block pattern we discussed in the previous video to open a file called novel.txt. You might also guess that using the write method on a file object writes contents to it instead of reading from it. The second argument to the open method is new though. So, what does the W mean? File objects can be opened in several different modes. A mode is similar to a file permission. It governs what you can do with a file you've just opened. By default, the open function uses the R mode, which stands for read only. You get an error if you try to write to a file open in read only mode. Since read only is the default, we don't have to pass the R as a second argument when we just want to read the file. Writing, however, is a whole different story. The W character tells the open function that we want to open the file for writing only. If the file doesn't exist, then Python will create it. If the file does exist, then its current contents will be overwritten by whatever we decide to write using our script. It's important to remember that when opening a file in write-only mode, you can't read its contents. If you try to, the interpreter raises an error. If you want to add content to a file that already exists, you can do that by using other modes, like A for appending content at the end of an existing file, or R+ for read-write mode, where you can both read contents and overwrite it. This has tripped up a lot of us more than once. So I'll say this again. If you open a file for writing and the file already exists, the old contents will be deleted as soon as the file is open. Yikes. Imagine accidentally deleting important content in a file. So remember, double check that you're opening the right file using the right mode. For example, if you're generating a log file of events that your program came across, you probably want to open the file using append, A mode. Opening it in write, W mode, would mean you'd write over any previous entries in that file. And that's not a good idea for a log file. Or if you're generating a report and want to write it out to a new file using the write, W mode, you probably want to check if the file exists to avoid losing any previous contents. We'll learn how to check if a file exists in an upcoming video. And finally, what's that lonely looking 30 doing hanging out at the end of our code? That's the return value of the write method. When successful, this method returns the number of characters that it wrote. So in this case, 30. Along with read-only, write, append, and read-write, the open function supports a bunch of other modes. You'll find all the documentation on this in the official reference, which we'll link to in the next reading. Okay, and breathe. Nice job. You just learned some complex things. It might not make sense right away, so have a look at the cheat sheet coming up, which puts all the information in one place for you. And remember, if you feel stuck at any point, you can always rewatch the videos or ask for help in the discussion forums. Over the last few videos, you learned how to open and read a file, how to iterate through a file, and finally, how to write a file. We use these operations a lot when working with files, so they're super important to know how to use. So, head on over to check out the cheat sheet now. And after that, we can get some hands-on practice with all this in a Jupyter Notebook. In earlier videos, we saw how we can read files, iterate through the contents of files, and also write contents of files. Those are the most common operations we'll do with files, but there's plenty of other things we might need to do when working with files in our scripts. We may need to delete, rename, or move files. Or we might need information about a file, like the time it was last modified or its current size. Let's explore some of the many things that we can do with files in Python. For these operations, we'll be using functions provided by the OS module. This module provides a layer of abstraction between Python and the operating system. It allows us to interact with the underlying system without us knowing whether we're working on a Windows, Mac, Linux, or any other operating system supported by Python. This means that you can write and test a script on one operating system, like Windows, and then run it on a different operating system, like Linux. But one thing to watch out for, paths can be different across different operating systems. So, whenever we're using an absolute path in our code, we need to make sure we can provide alternatives for the platforms we want to support. The OS module lets us do pretty much all the same tasks that we can normally do when working with files from the command line. We can change a file's permissions and delete or rename files through our code. This means you can write scripts to do these operations for you automatically. I bet you're already thinking about how useful the OS module is going to be in your IT role. To delete a file, we can use the remove function from the OS module. Let's see this in action. So, we first import the OS module. Then, we call the remove function the OS module gives us and pass the string novel.txt, which is the file we created earlier. The file's now been deleted. Let's see what happens if we try to remove it again. Fail. If we try to remove the file that doesn't exist, the function will raise an error. We've got a file not found error. The error type's pretty explanatory. And the message also tells us the name of the file it couldn't find, novel.txt. We can easily rename a file with the rename function. The first parameter to the rename function is the old name of the file, and the second is the new name. Let's check it out. Yep, in Python, it's that easy to write a masterpiece. If we try to do this for a file that didn't exist, we'd get a file not found error again. So, how do we check if the file exists or not? There's a submodule inside the OS module for dealing with things related to file information, like whether they exist or not. This is called the OS path submodule. And we can use the exist function in this module to check whether a file exists. Let's try this out with a couple of examples. In this example, the exist function returned a value of true, telling us that the finished masterpiece.txt exists. But userlist.txt doesn't exist, so the function returned a value of false. The exist function is super useful. We can use it to check that a file exists before trying to read it, or verify that it doesn't exist before trying to write it, which helps us avoid losing any data. Python gives us some basic ways to interact with files stored on a computer. We're going to take a look at them in our next video. We'll cover how to get other information from files, like their size, the last time they were modified, and a bunch more info. See you there. We saw earlier how to manipulate files with functions like osRename and osRemove, and how to check whether the file exists using osPathExist. We can get a lot more info about our files using functions in OSPath module. For example, to check how big a file is, we can use the getSize function, which returns the file size in bytes. To check when a file was last modified, the getMtime function comes in really handy. Let's check out how this works. Huh? What's that long number? It doesn't look like time, does it? That's because it's a timestamp. In this case, specifically, it's a Unix timestamp. It represents the number of seconds since January 1st, 1970. Seems a bit random, right? But there's actually a really good reason behind this date. This was adopted years ago to store the times associated to files in computers. Since that's when they started publishing Unix operating systems, Unix uses that date because there couldn't be any file created before that time. While Unix timestamps have a 50-year history, they're still very much present today. They're used by file systems to show when a file was created, accessed, or modified. They are also used in other systems, like databases. As an IT specialist, you're bound to run into them in your day-to-day. But despite all of that, the number is pretty hard to make sense of. We can use the datetime module to make it easier for us humans to read, like this. Here, we're using the fromTimestamp method of the datetime class inside the datetime module. It makes the date far easier for us to understand. Remember, the functions in the OSPath module take the info provided by the operating system so that we can use it in our scripts, no matter what OS we're running. We can check a file's size or last modification date without having to know the operating system the machine's running, or the type of file system that the file's stored in. Nice, right? Another cool feature of the functions is that we can work with both relative and absolute paths. In our examples, we've been using the relative file names without having to specify their full paths. In some cases, we may need to specify exactly where the file is to work with it in our script. This is where the absPath function can help. The absPath function takes the file name and turns it into an absolute path. Python uses the current working directory, which is where the script is being run, to start looking for the file and construct the full path that identifies it. This is useful if we want to store the file's full path or access a file no matter what the current directory is. There's a ton more functions in the OS and OS Path modules that let us work with files. But don't worry, you don't have to learn them all by heart. Whenever you need to do something with files, it's a good idea to check the documentation and research what functions are available to find the ones that you need. You'll find a link to the documentation in our next reading. Wow, we're steaming right along now. We've seen how to read, iterate through, and write files. We then learned how to manage files using lots of useful methods. Now is a good time to try our examples on your computer, or maybe even come up with your own to really get a grasp of it all. So, no rush, you'll find me in the next video whenever you're ready. There, we'll dive into how to work with directories in our scripts. If you need to work with files in your scripts, odds are you'll have to handle directories too. For example, you might need to process all the files that are in a specific directory, or generate a directory with the results of your data analysis. As with files, Python provides a bunch of different functions that let us create, delete, and browse the contents of directories. You might remember when we talked about the current working directory, and how important it is to know this when using a relative path to determine the location of a file. To check which current directory your Python program is executing in, you can use the getCwd method. If you use a Unix-like system, you might remember that the name of the command that prints the working directory is called pwd. In this case, the current directory is our user's home directory, which is the default directory we start on when opening a terminal in Linux. To create a directory, we use the makedir function. This function has the same name as both the Windows and Linux commands that do the same exact thing. So, we've just created a directory called new_dir, and it's located in the current working directory. You can also change directories in your program by using the chdir function and passing the directory you'd like to change to as a parameter. Just like the other functions we've seen, we can use relative or absolute paths to do that. As you can see, we've changed the current working directory to the new directory that we created inside the user's home directory. We use mkdir to create directories, and we can use rmdir to remove them, like this. But the rmdir function will only work if the directory is empty. If we try to remove a directory that has files in it, we'd get an error. We need to first delete all the files and subdirectories in that directory before we can actually remove it. But how can we find out what contents are in that directory? Well, there are a few techniques that we can use to do this. The oslistdir function returns a list of all the files and subdirectories in a given directory. Let's see how this looks for a website directory. So, we got a list of strings. Since they're just strings, we don't know if they're directories or files. To find out what they are, we can use functions like ospathIsDir. But before we look at how that works, see how the list contains just file names? If we want to know whether one of these files is a directory, we need to use ospathJoin to create the full path. Let's see all of this in action now. This code is doing a bunch of interesting stuff, but let's go through it step by step. First, we're defining a dir variable with the name of the directory that we want to check. This makes our code more readable and more reusable. Then, we're iterating through the file names returned by the OS listdir. We know from our previous execution of this function that these are just the names of the files without the directory. So, using OS path join, we join the directory to each of those file names and create a string with a valid full name. Finally, we use that full name to call OS path isdir to check if it's a directory or a file. Maybe you're wondering what's up with that join function. It seems to just add a slash between two strings, right? Well, the join function lets us be independent from the operating system again. In Linux and Mac OS, the portions of a file are split using a forward slash. On Windows, they're split using a backslash. By using the OS path join function, instead of explicitly adding a slash, we can make sure that our scripts work with all operating systems. It's another one of those handy little tools that help us avoid errors when working on different platforms. As we called out earlier, there's a lot of functions to manage directories in Python, and we only covered a handful here. We'll learn some others throughout the course as we need them. Wow, this stuff sure is a bit complex. Great job sticking with it. Persistence and determination are key qualities for both IT jobs and learning to program. And you're showing me that you've got both by the bucket load. The more comfortable you are with what you've learned so far, the easier it'll be to learn new stuff coming up. So take the time now to review and practice everything before moving on. You'll find a cheat sheet in the next reading to help you do just that. So be sure to check that out, and then head on over to the quiz and check in on how much you've learned. When we first talked about how to read files, we looked at files with lines of text, one after the other. This is useful in a bunch of different situations, since lots of programs store their state in text files, and we can also handle configuration files and log files as text. But data comes in a bunch of different formats besides text, and you may need to deal with some of these in your scripts. Formats give data structure, and remember that computers love structure and precision. To be able to process a data set, it helps to know ahead of time how that data set will be arranged. If you can expect data to be represented in a certain way, it's easier to extract meaning from it. Let's look at a very simple example. If we have a file that contains one line per machine and details the users that are logged into that machine, then when we read the file, we know how to parse it to get the information that we want. Parsing a file means analyzing its contents to correctly structure the data. We use a bunch of different file formats to structure, store, and transport data. You might be familiar with some already. For example, HTML is a markup format which defines the content of a web page. JSON is a data interchange format commonly used to pass data between computers on networks, especially the internet. CSV, or comma-separated values, is a very common data format used to store data as segments of text separated by commas. In the Python standard library, you'll find classes and modules for working with many of these data formats, including CSV and HTML. For less common file formats or more advanced manipulation techniques, you'll find more libraries available as additional Python modules. In the next few videos, we'll check out how we can use a CSV module to process CSV files. This not only shows how we can use Python to work with a specific data format. Knowing how to work with CSV files is a pretty useful skill to know. This format lets us easily store and retrieve information that we might need for our scripts, like employees in our company or computers in our network. In my job as a system administrator, I create CSV files when I want to convert the output of a command into a format that will be easier to parse later on. For example, the df command prints the currently used disk space in a format that's easy to read by human eyes. But turning the info into a CSV makes it much easier to work with the data in my scripts. A lot of programs are capable of exporting data as CSV files, such as spreadsheet applications like Microsoft Excel or Google Sheets. It can actually be helpful to think of a CSV file like it's a spreadsheet, where each line corresponds to a row and each comma-separated field corresponds to a column. So, now that we know what CSV files are, let's learn how to read them. Like we said, CSV stands for comma-separated values. CSV is a pretty simple format. These files are stored in plain text, and each line in the CSV file generally represents a single data record. Each field in that record is separated by a comma, with the contents of the field stored between the commas. For example, if we're storing information about employees at our company, we might store the data like this. Looking at this example, the line that starts with Sabrina is a data record, and the name Sabrina Green represents a name field, followed by a phone number field and a role field. Python's standard library includes a module which lets us read, create, and manipulate CSV files. Do you want to guess what that module is called? If you guess CSV, you're right. All these self-explanatory names makes life a lot easier, right? So, we'll be using the CSV module, and to do that, we'll need to import it, like we've been doing with the other modules. Now, before we can parse a CSV file, we need to open the file, the same way as before. And now we can parse this file using the CSV module. Okay, that's given us an instance of the CSV reader class. We can now iterate through its contents and access the information that it parsed. Now, the row variable will hold each row in the CSV file. This variable is a list, with each field in the CSV corresponding to one element in the list. We know from before that the first field is the name, the second one the phone number, and the third the role. So we can unpack the values so that we can use variables to refer to them. Remember that for this to work, we need to have the exact same amount of variables on the left side of the equal sign as the length of the sequence on the right side. Now that we've unpacked these values, let's print them to the screen. As we mentioned, we unpack the row so that we don't have to use indexes to access each element in that list. For example, we could have used row 0 to access the name of the employee. This is valid, but it can be hard to follow when reading a lot of code. Unpacking the list into named variables makes the code easier to understand later on. And before we forget, let's close this file now that we're done with it. Pretty useful, right? With that, we've now learned how to read and iterate through CSV files. Up next, we'll talk about how you can generate your own CSV files. In the last video, we used the reader function from the CSV module to read the contents of a CSV file. Similarly, we can use the writer function to generate contents to a file. This can be really helpful if you process some data in your script and you want to store it in a file. Maybe you want to import it into a spreadsheet or use it later on in your script. We'll start by storing the data that we want to write into a list. We've created a list of lists. This is the data that we want to store in the CSV file, representing the names of the machines in our network and their IP addresses. All right, with that data ready to be written, let's open the file in write mode. We'll use the with block that we saw before, so we don't forget to close the file. Okay, now that we have the file open for writing, let's call the writer function of the CSV module with this file as a parameter. The writer variable is now an instance of the CSV writer class. There are two functions that we can use: write row, which will write one row at a time, and write rows, which will write all of them together. In this case, we already have all the data that we want to write, so we'll call write rows. Nice. With that, we've written our data to the CSV file. Before we move on, let's see how this looks when we use a tool outside of Python, like the cat command. All right, our code worked and we generated a CSV file with the data that we wanted. Nice work. We're on a roll, so let's keep going. In the next video, we'll learn how to read and write CSV files with dictionaries. I'll see you there. In our earlier examples, we saw how we can read and write CSV files, and we use list as a data type on the Python side. This works when we know what the fields are going to be, but it can be pretty cumbersome when we have a lot of columns and we need to remember which is which. Imagine if your list of employees not only had name, phone number, and role, but also start date, username, office location, department, preferred pronouns, and so on. It would soon get hard to keep track of which column corresponds to which position in the row. For cases like this, it's common for CSVs to include the names of the columns as the first line in the file, like in this example. This CSV file lists a bunch of internally developed programs used at the company, including the latest version, the current development status, and the number of people using it. Check out how the first line of the file includes the names of each of the fields. We can profit from this additional information by using DictReader, a slightly different reader that's also provided by the CSV module. This reader turns each row of the data in a CSV file into a dictionary. We can then access the data by using the column names instead of the position in the row. Let's see how that looks. So here, we're opening the file and creating a DictReader to process our CSV data. Then, when going through the rows, we can access information in each row using the keys, just like we would when accessing data in the dictionary. See how we use row name and row users to get the name of the number of users? Let's execute this and see what happens next. As you can see, we've successfully printed the contents of the two fields that we wanted. Two important things to call out here. One, the order of the fields in the file doesn't matter. We can just use the name of the field instead. And two, Chatty Chicken is still an alpha, so only has 4 users. But you know, with a name like that, it's going to be a hit. So we can use DictWriter in a similar way to generate a CSV file from the contents of a list of dictionaries. This means that each element in the list will be a row in the file, and the values of each field will come out of each of the dictionaries. For this to work, we'll also need to pass a list of the keys that we want to be stored in the file when creating the writer. Let's see this in action. First, we need a list of dictionaries with the data that we want to store. For this example, we want to store data about the users in our company and the departments that they work in. So, here we have our list of dictionaries, and each contain the keys name, username, and department. We now want to write this to a file, and the code will look like this. So, we first define the list of keys that we want to write to the file. Then, we open the file for writing. Next, we created the DictWriter passing the keys that we had identified before. And then we call 2 different methods on the writer. The writeHeader method will create the first line of the CSV based on the keys that we passed. And the writeRows method will turn the list of dictionaries into lines in that file. Let's check if this worked correctly. All right. We successfully generated a CSV from our dictionary. Nice, right? Let's take a moment to acknowledge everything you've learned about managing files over the last few videos. You can read, write, and work with files and directories. And now you can also read and write CSV files. You started this course with fundamental knowledge of Python, and you've progressed so much in just a few videos. Remember, we don't expect you to learn everything by heart. You'll pick it all up with practice, which is why, up next, we've got another cheat sheet for you. In it, you'll find a rundown of everything we just covered, so you can refer to it whenever you need a little refresher on working with CSV files. After you check that out, head on over to the quiz and put your new knowledge to the test. Awesome! You've made it to the end of the module, and you now know a whole lot more about how to manage files with Python. Take a sec to congratulate yourself. Some of these concepts might seem difficult now, but you'll see how quickly your confidence develops once you start managing files on your own. These are super useful skills that you're picking up. In the past few videos, we checked out how to read and write to both text and CSV files, and how to manage files and directories with Python. We've covered a lot, but really, we've only scratched the surface of all the different things that we can do with files and directories. Keep in mind that files are one of the most important ways of storing and transmitting information in IT. There are more file formats, more ways of iterating through directories, and more tools to help us get things done. As we called out earlier, the Python standard library includes modules for manipulating only some data formats out there. There's a bunch more data types the standard library doesn't cover. If you need to do work with a different format or do something more advanced than what the standard library provides, you can always use one of the many external Python modules available on PyPy. Throughout the rest of the course, we'll be using what we've learned so far and checking out more tools and functionality that are available to operate with files and directories in Python. But before moving on to our next subject, we've got a graded assessment for you to tackle. Again, you'll be using QuickLabs to simulate a real-life scenario. We'll give you some data files that you'll need to process, and then you'll write a script that takes the info and uses it to generate a report. Nervous? Don't be, you got this. And if you need to go back and review any of the videos, then take your time. I'll be here waiting for you after you finish your assessment. Now go, get after it. Welcome back, and congratulations on completing that second lab. Did you find it difficult? Was it a breeze? Was it fun? Come on. I know you're having some fun. This is some really cool stuff you're learning. Of course, with anything new, you might struggle a little bit in the beginning, but we're getting there. Remember, it's okay if some things weren't completely clear from the get-go. By writing your own scripts, you're getting the practice that you need to become really good at this. The more scripts you write, the more natural it will all become. In the last module, we looked at how we can manage information in files. We saw a bunch of different examples of applying functionality to automation. We looked at CSV files in particular, which can be used to store and process interesting data. In this module, we'll take our data processing abilities one step further and learn about regular expressions, which are a very powerful tool to add to your IT toolbox. With regular expressions, we'll be able to find and operate on text in a more flexible way than we have up until this point. This is a complex subject, I'm not going to lie. So if at any time you feel lost or overwhelmed, you can always rewatch the videos. Also, make sure that you practice the examples in the videos and try coming up with your own. And always feel free to share your triumphs and tribulations in the discussion forums with your fellow students. Awesome. We've got a bunch of exciting stuff to dive into. Are you ready? All right, let's get to it. We said we'll be talking about regular expressions. So what are these expressions and why are they regular? A regular expression, also known as regex or regexp, is essentially a search query for text that's expressed by a string pattern. When you run a search against a particular piece of text, anything that matches a regular expression pattern you've specified is returned as a result of the search. Regular expressions let you answer questions like, what are all the four-letter words in a file? Or, how many different error types are there in this error log? In other words, regular expressions allow us to search a text for strings matching a specific pattern. Knowing about regular expressions can be useful for anyone who needs to perform text processing. From IT specialists to software engineers, system administrators, and data analysts, a working knowledge of regular expressions is a handy tool to, well, have handy. As a system administrator, I use regular expressions when I need to pull information from a file that has other information in it. For example, if I have a file that lists NFS mounts and options, and I want to pull only the server name, I can write a regular expression that strips each line of the excess data and returns only a list of the information I need. Regular expressions are a pretty big topic in IT. In this course, we'll aim to cover the most important parts, but we won't go through them all. For your scripts, basic regexes will usually be enough to get you started, and they'll enhance your program's ability to process text. With time and practice, you'll pick up even more advanced techniques. There are lots of different ways that we can apply regular expressions. We can use them in a whole wide range of programming languages, which of course includes Python. We can also use command line tools that know how to apply regexes, like grep, sed, or awk. We can even use regular expressions inside text processing tools, like code or document editors. As with other widely used technologies, there's a broad range of tools that incorporate regular expressions, and implementation details may vary from tool to tool or language to language. But thankfully, the principles are always the same. Once we learn the basics, we can very quickly apply the same concepts to different applications. Over the next several videos, we'll explore the Python module that deals with regular expressions. We'll check out how we can apply the regexes to processing, parsing, and extracting meaning from text read by our scripts. And we'll look at a bunch of different examples where we can use regular expressions to solve some real-world problems. Are you as eager to get going as I am? Great, let's go. At this point, you might be wondering, why do I need more processing power than just looking for strings in a text, which I already know how to do in Python? The answer lies in the power and flexibility of regular expressions. For example, let's say we have log entries with a typical log line format, like this one. We want to extract a process identifier from this line, which is a number between the square brackets, 1, 2, 3, 4, 5. There's a lot of extra text in this log line that we don't need, like the date, the computer name, and other info. We could extract a process ID by using the index method to find the first square bracket in the string. Remember that when accessing strings, the index of the character is the position of that character in the string, starting from 0. In this example, the index of the first square bracket would be 39. If we don't want to capture the square brackets, we will start at the next position and include 5 more characters after that. Let's give it a go. Although we get the text that we wanted, we might hit a few bumps down the road. Can you spot them? One problem is we don't know for sure how long the process ID string will be in all cases. In this example, we can see that it's 5 characters long, but that may change in the future if the computer is restarted, or the number of processes increases. This could also break if, for any reason, the line includes another square bracket before the process ID. So it's a solution, but it's a very brittle one. Any other ideas? Instead, we could use a regular expression to extract the process ID in a more robust fashion. For that, we're going to import the RE module, which lets us use the search function to find regular expressions inside strings. Great! This regular expression will work, no matter where our process ID shows up or how long or short the line is. As long as there's a single sequence of numbers in the string marked by square brackets, this regex will extract those numbers for us. If the regular expression stored in the regex variable looks like gibberish at this point, don't worry, that's expected. We'll explore the syntax and how we use these expressions in upcoming videos. At this point, the key takeaway is that regular expressions are both powerful and flexible tools. By the end of this module, you'll be able to read and unpack statements like the one in this example. We're off to a strong start. Next up, we'll learn how to use some very basic matching with the grep command. In our last example, we used a pretty complex regular expression from a Python program to look for a process ID. This is just one example of something we might want to do when processing text from our Python scripts. We can also use regular expressions with a bunch of command line tools. grep is an especially easy to use yet extremely powerful tool for applying regexes. It's a great way to easily try out some expressions and get familiar with them. So let's look at some basic matching we can do with grep. The simplest of all matchings is just to search to see if the string is present. Remember that grep works by printing out any line that matches the query that we pass it. So for our simplest query of passing a plain old string, grep will print any lines containing that string in the file that we give it. Let's try this out using grep to find words inside the /user/share/dict/words file, which is a file that some spell checking programs use to verify if a word exists or not. This file contains one word per line. We'll start by looking up words that contain the particle thon. Let's see what happens. So, when we call grep with thon as the pattern to match on, and we pass our list of words as the file, we see that it matches with a bunch of different words. These words all contain the string thon somewhere inside of them, which is why they appear in our results. We also see that the output is highlighted for us, showing us the matching part of the line in a different color. This added visual indicator is something that grep does for us so that we can easily see where the match occurred. It's worth calling out that the string we're passing to grep is case sensitive, so it needs to be matched exactly. If we use uppercase letters, they'll only be matched by uppercase letters. If we wanted to match a string regardless of case, we will have to pass the -i parameter to the grep command, like this. Nice! So we now know that any basic string is already a regular expression, which will match a line that contains that string. To get the most out of regular expressions, we need to learn more of their syntax, which can be as complicated as it is powerful. In particular, we have to know the reserved characters that give extra meaning to the patterns that we create. It's these characters that allow us to do more advanced matching than just checking for a literal string. For example, a dot matches any character. This means that if we include a dot in our expression, that dot is a wildcard that can be replaced by any other character in the results. Let's check out an example of this. Here, we're looking for the pattern L.RTS within the list of words. This pattern matches 3 different words: alerts, blurts, and flirts. Check out how for each of those words, the dot in our pattern was substituted by a different letter. Are you starting to see the power of regular expressions? With them, we can find portions of text that match a given pattern, even when the pattern isn't a whole word. We could use this, for example, to look for entries in a log file that match a certain format, or to find rows in a CSV file that share the same characteristics, even if they're not exactly the same. Really helpful, right? Other easy examples of special characters that we can use in our regular expressions are the caret or circumflex and the $ anchor characters. These tell us where in the line the regex should match from. The circumflex indicates the beginning and the $ indicates the end of the line. For example, to look for all the words that start with a string fruit, we would write grep circumflex fruit and our file. See how regexes can be an extremely fruitful tool? Let's check out one more example. We'll use grep to find all the words that end with cat by writing grep cat $ and our file. That worked just perfect. Are you starting to get it, meow? One thing to remember is that the circumflex and the $ specifically match the start and end of a line, not a string. Take a log file, for example, where each line contains a lot of different words. We can use a circumflex to check if a line begins with a pattern, or use a $ to check if it ends with a pattern. But our patterns will match only if the line fits that criteria, not the contained words. There are many other characters like these, and we'll go over a bunch of them in the next few videos. But before moving on to more syntax and examples, it's time for a quick quiz. Welcome back. How are we feeling about regexes so far? Remember, this stuff is pretty tricky, so it's okay if it takes a bit of time for it to sink in. As we called out before, we use the RE module to apply regular expressions in Python. This module includes a bunch of different functions that can help manipulate strings. Let's see how we can use this module for some basic matching. So, we called the search function on the RE module and told it to use the pattern AZA on the string plaza. We then stored the return value of that function in the result variable. The R at the beginning of the pattern indicates that this is a raw string. This means that Python interpreter shouldn't try to interpret any special characters and instead should just pass the string to the function as is. In this example, there are no special characters. The raw string and the normal string are exactly the same. But it's a good idea to always use raw strings for regular expressions in Python. So, we'll be using raw strings in all of our examples. With that said, let's print the result of the variable and see what we get. Great, our result is a match object. The output we get when calling print already shows some interesting information, like the position in the string that matched and what the actual matching string was. Let's try this out again with a different word. In this case, we can see that the span attribute is different. That's because the match substring is in a different position inside the string. The match substring is still the same though, because we're matching with a plain string, no special syntax yet. What do you think will happen if we pass a string that doesn't match the expression? Let's try it and find out. Did you guess right? If the expression doesn't match the string that we pass, we get none as a result. Remember, none is a special value that Python uses to show that there is not an actual value there. So when we're applying regular expressions, we now know that if the search function returns none, it means it didn't find a match. Let's practice the special characters that we've seen up until now with a few examples. Here, we told the search function to use the circumflex X pattern on the string xenon. We can see that it matched at the beginning of the line on our X as we expected. What happens if we use a dot, which can match any character? Now we're using p.ng as a search pattern. It matches the word penguin that we're passing, and in the match object, we see the matching string is peng. Let's try it out with a couple other strings. Nice. So here we can see the match attribute always has the value of the actual substring that matched the search pattern. And the span attribute indicates the range where the substring can be found in the string we passed. We can also pass additional options to the search function. For example, if we want our match to be case insensitive, we can do this by passing the re.ignore case option. Great. Now we know how to apply in Python the basic regular expressions that we used earlier with the grep command. You can now use your local Python installation to practice these and any other examples of regular expressions that you can think of. So, how about experimenting on your own until you feel comfortable with them? Take your time, you'll get the hang of it. Coming up, we're going to dive deeper into the syntax of regular expressions and what we can do with them. We've seen by now how we can use a dot in our regular expressions as a special character that can match any character. In the regex world, this is known as a wildcard because it can match more than one character. Using a dot is the broadest possible wildcard because it matches absolutely any character. But what if we wanted something stricter? Like checking if an answer given by a user contains a valid character, or finding all the usernames in a CSV file that start with a vowel. We have to restrict our wildcards to a range of characters to do this. For this task, we use another feature of regexes called character classes. Character classes are written inside square brackets and let us list the characters we want to match inside of those brackets. For example, say we want to match the word Python but allow for both lowercase or uppercase p. We could do it like this. Inside the square brackets, we can also define a range of characters using a dash. For example, we could use lowercase a to lowercase z to state any lowercase letter. So, if we wanted to look for the string way preceded by any letter, we could write the expression like this one. Cool, we got a match. The character class defined was matched by the letter H. Let's try a different string. Dang, in this case, we didn't get a match. That's because the string way is preceded by a space, and that doesn't match the range that we defined. We can define more ranges like uppercase A to uppercase Z for all uppercase letters, or 0 to 9 for all digits. We can combine as many ranges and symbols as we want, like this. So, as you can see, we can match anything that's defined between the square brackets. It's pretty cool, right? While this is super useful, sometimes we may want to match any characters that aren't in a group. To do that, we use a circumflex inside the square brackets. For example, let's create a search pattern that looks for any characters that's not a letter. Here, our pattern matched the first space in the sentence. What if we also add a space to the list of characters that we don't want to match? You might have guessed this. Because we added a space inside the character class, our example now matched the final dot in the sentence, which isn't in the list of characters to exclude. If we want to match either one expression or another, we can use the pipe symbol to do that. This lets us list alternative options that can get matched. For example, we could have an expression that matches either the word cat or the word dog, like this. So, since the string contains a substring cat, the search function could find it. Let's try an example with dog. This expression contains the substring dog, so we found a match. Let's try a sentence with both dogs and cats. In this string, we actually have two possible matches for our search, but we only get the first one. That's the way the search function works. If we want to get all possible matches, We can do that using the findAll function, which is also provided by the RE module, like this. So with findAll, we don't need to choose between cats and dogs. What a relief. Okay, we've seen how we can match different groups of characters or even completely different strings. Are you starting to wrap your head around it all? Like I said before, this stuff is kind of tricky. Feel free to take time to practice these functions on your own. These tools can be super useful in the IT world, so you'll definitely want to get a good handle on them. Now, what do you think we'd have to do if we wanted to match something more than once? Once you're ready, meet me in the next video to find out. So far, we've looked at how to match one specific character, a group of characters, or even any character. Now we're going to check out how to match these characters several times. Say we wanted to find the longest word in a string, or we wanted to find the host names in a log file by checking for a bunch of alphanumeric characters between brackets. We can do this using another interesting regex concept, repeated matches. It's quite common to see expressions that include a dot followed by a star. This means that it matches any character, repeated as many times as possible, including 0. Let's see a couple of examples of this. In plain English, you could read this regex as match pi followed by any number of other characters followed by n. But with our dot star combination, we expanded the range of the match to the whole word. See how the dot takes a different value for each letter? Let's try a different string, Python programming. What do you think the pattern will match? Huh? You might not have been expecting that. Remember, the star takes as many characters as possible. In programming terms, we say that this behavior is greedy. It's possible to modify the repetition qualifiers to make them less greedy, but we won't get into that now. To learn more about that, check out the next reading. But back to our example. While our pattern could have matched the word Python, it expanded all the way until the last n in the string. If we only wanted our pattern to match letters, we should have used the character class instead, like this. Remember how we said that 0 times is also a possibility? That would let the string pin also match our pattern. Let's try that out. As we called out earlier, implementations of regular expressions aren't always the same. Repetition qualifiers are one way they differ. Some implementations, like the one used by grep, only include the star qualifier that we just discussed. You can do a lot with just the star qualifier, so that's usually good enough. Other implementations, like the one used by Python or by the egrep command, include 2 additional repetition qualifiers, plus and question mark, that can help us construct more complex expressions. Let's check that out. The plus character matches one or more occurrences of the character that comes before it. Say we had the pattern O plus L plus. Let's check it against a few words. In this case, there was one occurrence of each, and the match pattern shows us the shortest possible matching string. Here, there were 2 of each. Again, we can see the match is a whole string that matches the condition. Let's try something that doesn't match. So, while our string here had an O and an L, it had another character in between them. Because of this, it doesn't match the search pattern. Does that make sense? The question mark symbol is yet another multiplier. It means either 0 or 1 occurrence of the character before it. Let's see how this works. The P wasn't present, but with the question mark, we marked it as optional, so we still got a match. Let's see what happens when the P is present. Great, the P was present and so the match included it. Nice job. You're moving right along through basic regular expressions. If anything's not clear, take some time now to check out the examples in your local Python environment. I bet you'll get it all down pat once you've tried things out for yourself. You just learned about repetition qualifiers, and we saw how there's a bunch of special characters to match different kinds of strings. But what happens when we want to actually match one of those characters, like a $ or a question mark? Well, lucky for you, we're going to find out in the next video. We've now seen a lot of special characters that we can use in our regular expressions to make them match different kinds of strings. Dot, star, plus, question mark, circumflex, $, and square brackets. But what can we do if we need our pattern to match one of the special characters? Say, for example, that we wanted to check that a certain string contained a dot as part of it. If we just put a dot there, it would match any character. Here, we wanted to match on strings that had .com in them, but we matched a string with something else in it. That's not what we wanted. To match an actual dot, we need to use an escape character, which in the case of regular expressions is a / character. So let's add that to our pattern. By escaping the dot, it no longer matched the word welcome. And since there's no .com in the string, it returned none. Let's try something that should actually match. Great. By adding the \, we've got this to correctly match what we wanted it to match. We can use the \ in this way to escape any special characters, including the ones that we haven't even talked about yet. Something to watch out for. It can get really confusing with backslashes since they're also used to define some special string characters. We've called out, for example, that \n is a sequence used in Python to indicate a new line, and \t does the same for tabs. When we see a pattern that includes a \, it could be escaping a special regex character or a special string character. Using raw strings, like we've been doing, helps us avoid some of this possible confusion, because the special characters won't be interpreted when generating the string. They will only be interpreted when parsing the regular expression. On top of this, Python also uses the \/ for a few special sequences that we can use to represent predefined sets of characters. For example, \w matches any alphanumeric character, including letters, numbers, and underscores. Let's check out a couple of examples. As we said, \w matches letters, numbers, and underscores. So, in the first example, our pattern matched the first 4 letters until the space, because spaces aren't part of that set of characters. While in the second example, it matched the whole string. There's also \d for matching digits, \s for matching white space characters like space, tab, or new line, \b for word boundaries, and a few others. Yikes, that was a lot. You might be thinking, escape, escape, escape from all these escape characters. If this sounds like a spaghetti mix of new characters, don't worry. You don't need to memorize them all. You can always consult our cheat sheet or other similar references that tell you which sequence represents which characters. And another great resource for testing out your regular expressions is a website called regex101.com. You can use this to try out your regexes, analyze each part of the expression, and figure out what's up with them when they don't work. You're doing an amazing job with all of this, and it's about to pay off. Up next, we're going to start creating some complex patterns and use them in real-world applications. So, meet me over in the next video. we've now looked into a bunch of syntax for using regular expressions in Python. Armed with all this knowledge, we can start combining these special characters to create patterns to match the text that we want. For example, say you had a list of all the countries in the world and you wanted to check which of those names start and end in A. What would the pattern look like? Maybe something like this: uppercase A, dot, star, lowercase a. Let's try that one out. Awesome, seems like that worked. Let's try it with a different country, Azerbaijan. Surprising maybe? This happened because we didn't specify that we wanted our pattern to match the whole string. So, while Azerbaijan doesn't finish with A, it does have an A in its name, so it matches our pattern. We need to make our pattern stricter by adding the beginning of a line and end of a line characters. By adding a $sign to our pattern, we've made it clear that we only want to match lines that begin and end with the letter A. So, Azerbaijan doesn't match anymore. Let's check that it still works for a country that should match, like Australia. Using regular expressions, we can also construct a pattern that would validate if a string is a valid variable name in Python. Do you remember what the rules were? It can contain any number of letters, numbers, or underscores, but it can't start with a number. So, what do you think the validating pattern would look like? We said it needs to start with a letter, so we'll start with a circumflex to indicate that we want it to start from the beginning. And now, a character class with all lowercase and uppercase letters plus the underscore. The rest of the variable can have as many numbers, letters, or underscores that we want. So, we need another character class, this time containing numbers, with a star at the end. Okay, we're almost done. You definitely deserve a star at the end of this. One last thing. We want this to be the end of the string that we're matching. Otherwise, we could match something that could be a variable, but that also contains additional stuff after it. So, we finish up with a $sign. Now, we'll apply this pattern to a few examples and check that it matches correctly. That's right, we can use underscores anywhere in the string that's a valid variable name. It matches our validation pattern because we included underscores in it. Let's try something a little different. Once we use a space, it stops being a valid variable name. It doesn't match our pattern because spaces aren't included in the possible characters. Let's check out a variable with a number. Sure enough, we can use numbers inside the variable name. Our pattern includes all numbers as part of the variable. But what if we start with a number? The variable with a number at the beginning isn't a valid variable name, and our pattern doesn't match it because the first of two character classes doesn't include numbers. Awesome job! We've covered the basics of regular expressions. There's still some more special characters to learn about and more interesting things that we can do with them, but I'm sure you're starting to already see the processing power that regexes bring and how they're another super useful tool to have in your IT toolbox, right? This was some complex stuff, but it can also be fun. Why not take a little time now to play around with the characters that you just learned to see what results you can get with them? Remember, practice builds comfort, and these little characters pack a powerful punch. They can help you out big time in your IT job, so they're worth buddying up to. Coming up, we've got a cheat sheet that summarizes all the syntax that we've seen up until now. Then you can put all of this new knowledge to the test with a quick quiz. Meet me in the next video once you're done. Up to now, we've used the search function to check if a string matched a certain pattern, but the only thing we've done with the result is print. Printing is useful when we want to see if a string matches a certain pattern, but most of the time, we want to take the information that we matched and use it for something else. For example, we may want to extract the host name or the process ID from a log line and use that value for another operation. For that, we need to use a concept of regular expressions called capturing groups. Capturing groups are portions of the pattern that are enclosed in parentheses. Let's say that we have a list of people's full names. These names are stored as last name, comma, first name. We want to turn this around and create a string that starts with the first name followed by the last name. We can do this using a regular expression with capturing groups. Let's see how this works. First, we'll create a matching pattern that matches a group of letters followed by a comma, a space, and then another group of letters. To capture our groups, we'll put each group of letters between parentheses, like this. Great, we have a match. Remember that \W will match letters, numbers, and underscores. The match object has more attributes and methods than the ones shown by print, so we're going to start using them now. Let's look at the output of the groups method. Because we defined two separate groups, the group method returns a tuple of 2 elements. We can also use indexing to access these groups. The first element contains the text matched by the entire regular expression. Each successive element contains the data that was matched by every subsequent match group. So let's look at the element at index 0. That's the whole string. Now, the following indexes correspond to each of the captured groups. Let's check this out. So we can construct the name that we want by using these indexes. Okay, so now that we've got this more or less working, let's put this into a function that would do the rearranging for us. We'll start by defining a function called rearrangeName that receives a name by parameter. Now we'll search the string with the same pattern that we saw before. If the result is none, it means it didn't match the format that we were expecting. So in that case, it would just return the name as it is. Okay, if we're here, then our pattern matched and our result variable will have 2 capture groups, one for the characters before the comma and another for the characters after the comma. Let's return the rearranged version of that string. Nice. We've defined our function. Let's test it out with a few names. Cool. This seems to be working, but what if we give it something a little bit more challenging? Now, the regular expression didn't match because we used the \W character, which only matches letters. And so it didn't recognize the middle initial as part of the given name. Can you figure out how to fix it? What we need to do here is add the extra characters that we want to allow in the names. In this example, we'd want to add spaces and dots. For other names, we can also include dashes. So after updating our pattern, this is what our function would look like. So, as you can see, by adding extra characters between square brackets, we rearranged a name that was a little more complex. I bet you can come up with some more examples for using capturing groups. Up next, we're going to cover more on repetition qualifiers. See you there. Up to now, we've used the star, plus, and question mark repetition qualifiers. What if we wanted a pattern that repeats a specific number of times? This could happen if we're processing a line that we know has some specific data in a column, or we know that we want a string of a specific length. In cases like those, we would manually write the same pattern as many times as we needed, but it would be hard to read and hard to maintain. And that's why Python also offers numeric repetition qualifiers. These are written between curly brackets and can be one or two numbers specifying a range. For example, to match any string of exactly 5 letters, we can use an expression like this one. Remember that the expression will match whichever part of the given string that fits the criteria. In this case, we're looking for letters that are repeated 5 times, and ghost has 5 letters, so it matched our pattern. In this string, we actually have more matches for our search, but we only get the first one. Remember what we can do to find more matches? That's right, use the findAll function, like this. Now we have an extra match for the word that's actually longer. What if we wanted to match all the words that are exactly 5 letters long? We can do that using \B, which matches word limits at the beginning and end of the pattern to indicate that we want full words, like this. We said that we can also have 2 numbers in the range. For example, if we wanted to match a range of 5 to 10 letters or numbers, we could use an expression like this one. These ranges can also be open-ended. A number followed by a comma means at least that many repetitions with no upper boundary, limited only by the maximum repetitions in the source text. Okay, that looks good. Pulse check. Hopefully Python isn't spooking you, and you're very much enjoying learning it. Wow, what is it about teaching Python that makes me break out these cheesy jokes? I can't help myself. Now, for our final example, a comma followed by a number means from 0 up to that amount of repetitions. Let's check that one out. Here, we looked for a pattern that was an S followed by up to 20 alphanumeric characters. So we got a match for strawberries, which starts with S and is followed by 11 characters. Whoa, that was a lot of repetition qualifiers. Ghosts and strawberries are fun and all, but we're ready now for a few more practical examples of how to use regular expressions. That's coming up in our next video. I'll see you there. Remember the example from the beginning of our discussion of regular expressions? It was way back in the first video of this module, when we were looking at the log lines and extracting process IDs. Well, we now have enough info to fully understand it. Let's walk through it step by step. The first character of the pattern is the backslash, which is used as the escape character. This means that the next character, which is a square bracket here, is treated literally for matching purposes. After the square bracket comes the first parentheses. Since it isn't escaped, we know it'll be used as a capturing group. The capturing group parentheses are wrapping the \d plus symbols. From our discussion of special characters and repetition qualifiers, we know that this expression will match one or more numerical characters. After the closing parentheses of the capturing group, we have the closing square bracket symbol, also preceded by the escape character. After calling the search function, we know that because we're capturing groups in an expression, we can access the matching data by accessing the value at index 1. Let's try our expression on a different string and check that it really works, no matter what the rest of the text is. Okay, this works fine. But what if our string didn't actually have a block of numbers between the square brackets? Darn, an error. What happened? We tried to access the index 1 of a variable that was none. And as Python tells us, this isn't something that we can do. So what should we do instead? We should have a function that extracts the process ID, or PID, when possible, and does something else if not. It's something like this. We'll start by defining a function called extract_PID. Now, we'll use the same regex as before, and we'll store the result of the search function in a result value, just like this. Now, we know that if the search wasn't successful, the result will be none. So we need to do something a little different here. What we choose to do depends on what we want the rest of the code to do. Let's say that if we couldn't find the PID, we'll return an empty string. And finally, if we're at this point, it means the result is a match object. So we can access the first capturing group and return that. We can now test our function with the original log line to check that it still does the right thing. Nice! Let's wrap this up by trying it out with a string that broke our code before. Great. It didn't match, so it returned an empty string. That's exactly what we wanted. All right. We now have a function that lets us correctly extract PIDs from log lines without it breaking other lines. Hopefully, this is all starting to make sense now. But remember, that if things are not totally clear, you can always review the content and practice on your own until you feel comfortable with it. Up next, for the last step in our journey with regular expressions, we'll check out some of the other functions the RE module gives us. Up to now, we've been using two functions from the RE module, search and find all. There are actually a few more functions that can be really handy, depending on what we're trying to do. One of these functions is called split. It works similarly to the split function that we used before with strings, but instead of taking a string as a separator, it can take any regular expression as a separator. For example, we may want to split a piece of text into separate sentences. To do that, we need to check not only for the dots, but also for question marks or exclamation marks, since they're also valid sentence endings. It's something like this. Check out how we're not escaping the characters that we wrote inside the square brackets. That's because anything that's inside the square brackets is taken for the literal character and not for its special meaning. Also, see how the notation marks aren't present in the resulting list. If we want our split list to include the elements that we're using to split the values, we can use capturing parentheses, like this. This gave us both the sentences and the notation marks as elements of a list. Another interesting function provided by the RE module is called sub. It's used for creating new strings by substituting all or part of them for a different string. Similar to the replace string method, but using regular expressions for both the matching and the replacing. Let's see this in an example. Say we had some logs in our system that included email addresses of users, and we wanted to anonymize the data by removing all of the addresses. We could do that by using an expression. The expression that we're using for identifying email addresses has two parts. The part before the @ sign and the part after it. Check out the part that comes before the @ sign. We include the alphanumeric characters represented by \W, which includes letters, numbers, and the underscore sign, as well as the dot, %, plus, and dash. After the @ sign, we only allow the alphanumeric characters, dot and dash. This will match all email addresses, as well as some strings that aren't really valid email addresses, like an address with 2 dots. In this scenario, we want to be better safe than sorry. So, we're going to redact anything that looks like an address. If we wanted to validate that the address is an actual email, we would need to be a lot stricter. We just use a regular expression for searching and a plain string for replacing. Let's now look at an example using sub where we use regular expressions for the replacing. For that, we'll go back to our code that switched the order of names of people and use sub to create the new string. So, once again, we've used parentheses to create capturing groups. In the first parameter, we've got an expression that contains the two groups that we want to match, one before the comma and one after the comma. We want to use a second parameter to replace the matching string. We use \2 to indicate the second captured group, followed by a space, and \1 to indicate the first captured group. When referring to captured groups, a backslash followed by a number indicates the corresponding captured group. This is a general notation for regular expressions, and it's used by many tools that support regexes, not just Python. We can also use them to match patterns that repeat themselves, which use capturing groups as back references. We won't look into them here, but if you want to learn more, you'll find a bunch more info about them online. Phew. And with that, we've wrapped up our overview of the power of regular expressions in Python. There were some things that we didn't get to cover, but our aim is to give you a foundation to build on. We hope that you've got a pretty good picture of the many things that we can do with regexes, and we encourage you to keep learning about them on your own. Now, as we've said, regular expressions aren't easy, but they're incredibly useful, so well worth the effort to master. To help you do this, we've got a practice quiz up next before you can jump into the next lab. Wow, what a journey these past videos have been. We've gone from knowing nothing about regular expressions to being able to do complex search and replacing in different kinds of text. We've covered a lot of really technical stuff in these videos, and you might be feeling a little overwhelmed. That's totally fine. Regular expressions can even make the most experienced system administrators sweat, and they can be tricky to get right. While regular expressions might be a bit confusing, don't let them intimidate you. They can save you a lot of time and effort if your script needs to process text. As with many things, the best way to get comfortable with regular expressions is to use them. Try out the examples we covered in these videos and invent your own regex patterns to see how they behave. You'll have another opportunity to practice regular expressions in the upcoming lab, where you'll put your newly acquired regex skills into practice to solve real-world problems. During the exercise, you'll be dealing with a CSV file, like you did in the previous lab. But this time, you'll use regular expressions to find the data that needs to be processed and operate on it. The time that you have for using virtual machines on Quick Labs is limited, so we do recommend that you try to solve the problem on your own computer first. Once you're confident with the code that you've written, go ahead and start the lab and put your code to work. I'll see you on the other side. Welcome back. Congrats on completing the last lab. You're making a ton of progress, and your horizons are expanding with each new tool that you learn. It must feel pretty gratifying to execute a script and see it perform how you expected it to, right? Well, hopefully you're starting to see more and more possibilities for automation as you learn some of the tools that Python offers. Let's quickly review everything you've learned so far in the course. First, you installed Python and set up your local environment. Then, we dove into how to manage files with Python. And finally, we started playing with regular expressions. In this module, we'll check out concepts that help us interact with the running operating system. And we'll look at how we can get the most out of the tools available. We'll kick this off by talking about how to read user data interactively. Then, we'll explore the standard input and output data streams provided by the operating system and see how we can interact with them, both from Python programs and from the system programs. In a lot of our examples, we'll interact with the operating system through the command line, so we'll start familiarizing ourselves a bit more with the Linux shell. We'll also talk about how we can execute system commands from Python. This allows our scripts to harness the power of the rest of the operating system. So it's important that we know how to manipulate the output of these commands and handle any generated errors. We'll wrap up by diving into one important source of information for IT specialists: log files. We already got a peek at a few log files in some of our earlier videos. Now, we'll look at how we can make sense of the information these log files provide by using the tools that we've learned throughout the course. So there's a bunch of interesting things ahead of us. Are you excited? 'Cause I'm excited. So what are we waiting for? Let's dive in. We've talked before about reading and writing files. Using files to store information and then processing that data with a script is a great way to build automation. But sometimes we need to interact with the user and ask them for certain pieces of information that just can't be stored in a file. To do this, Python provides a function called input. This function allows us to prompt the user for a certain value that we can then use in our scripts. Let's see what that looks like. Here we have a script called hello.py. It's a very simple script. It asks the user for their name and then prints the greeting that uses that name. Let's execute this script to see it in action. Hi computer. The input function always returns a string. If we want the data that we're reading to be a different data type, like a number or a date, then we need to convert the string to a format that we want. Let's look at a different example. This script does a bunch of things, so let's go over it piece by piece. First, we define a function that converts into seconds the number of hours, minutes, and seconds. The actual program starts by printing a welcome message and then entering a while loop. See how we first initialize the const variable that we'll use to check whether the user wants to continue or not? In the body of the while loop, we ask the user to provide the number of hours, minutes, and seconds for the conversion. As our toSeconds function requires integers, we're converting the value returned by the input function using the int function. With those three values, we then call the function and print the result. After that, we ask the user whether they want to do another conversion or not. Let's try the script out and see what happens. Great. Our code seems to be working properly. We entered 3 numbers and it did the right conversion. It's now asking us whether we want to continue or not. I think we have the time to answer, don't you? Let's say yes. This time, we said that we didn't want to continue, so the program finished and exited. And with that, we've seen how we can interactively ask the user for input. We're only a few minutes and seconds into this module, and you've already learned a new concept. Just imagine how much more you'll learn by the end of this module. Interactively asking the user for input might not always be the best approach for a problem we're trying to solve, but it's a great tool that you just added to your IT toolbox. We've now seen a couple of ways of getting information into and out of our scripts. We know how to read and write to files and accept input from the keyboard and print it to the screen too. But what exactly is going on behind the scenes when we do this? How does a Python program connect to both the screen and the keyboard? Well, it uses I/O streams. I/O streams are the basic mechanism for performing input and output operations in your programs. You can think of these streams as pathways between your programs and their input sources, like a keyboard, or output, like the screen. I/O streams aren't just available for Python programs. When we run a system command on our terminal, I/O streams are also being used to connect that command to the terminal input and output. This way, we can see the results of the command or enter data interactively if that's how the program works. We call these streams because the data keeps flowing. A program can read input and generate output as long as it needs to achieve its goal. Okay, but what do these streams mean in practice? Most operating systems supply 3 different I/O streams by default, each with a different purpose. The standard input stream, commonly referred to as stdin, is a channel between a program and a source of input, usually in the form of text data from the keyboard. When we use the input function to accept user input in a Python script, we're using the stdin stream. The standard output stream, or stdout, is a pathway between a program and a target of output, like a display. stdout generally takes the form of text displayed in a terminal, as is at play when we use the print function to write information to the screen. The last type of pre-made I/O stream is called standard error, or stderr. Standard error displays output like standard out, but is used specifically as a channel to show error messages and diagnostics from the program. It's usually printed to the screen. If you've ever run some Python code and received an error, then that error message was probably printed using standard error stream. Let's see this consolidated in an example. Our script here has 3 lines. Each line is interacting with a different stream. In the first one, we read from standard input. In the second one, we write to standard output. In the last one, we generate an error by concatenating a string to an integer. This error will be printed to standard error. Let's try it out. So, we first read some data through standard input and then printed it to standard output. Python then printed a type error because we tried to do something weird. As we called out earlier, these I/O streams aren't restricted to just Python programs. For example, we've been using the cat system command to display the contents of a file. When we do that, those contents are printed to the terminal using standard output, like this. And when one of these commands generates an error, that error is displayed to standard error. For example, if we use an unsupported flag with the ls system command, which normally shows the content of directories, we get this error. I know, it looks like standard output and standard error are the same here. That's because they both get displayed to the screen, but they're actually pretty different. We'll look into exactly how they're different later in the course. I'll keep you in suspense for now. We'll keep coming across these streams in our Python programs, so you'll start to become more familiar with them. And later on in the course, we'll even learn how we can redirect them to other files and other processes. The key takeaway for you to remember at this point is that I/O streams are ways for programs to give and receive information. In the next couple of videos, we'll take a look at other ways that we can provide information to our programs, environment variables, and command line arguments. When we open a terminal application on a Linux computer, whether it's local or a remote machine, the application that reads and executes our commands is called a shell. A shell is a command line interface used to interact with your operating system. The most commonly used shell on Linux is called bash. Other popular shells are ZSH and fish. While they operate in similar ways, for this and upcoming videos, when we talk about the Linux shell, we mean bash. Our Python programs get executed inside a shell command line environment. The variables set in that environment, which are called, you guessed it, environment variables, are another source of information that we can use in our scripts. Understanding and being able to change environment variables can be really useful to quickly alter a program's behavior. Usually, we can do this by just making some minor changes in the environment the programs are running in. From a command line prompt, we can check these variables using the env or env command. Let's take a look. Whoa, that's a lot of different variables. But what are they for? It all depends on the variable itself. Some are more important than others. For example, the path variable is a very important one. Let's print out the contents of just that one using the echo command. As a refresher, echo is a command that we use to print text in the Linux shell. And when we want to access the value of a variable in this shell, we need to prefix the name of the variable with the $sign. Here, we've printed the contents of the path variable. The shell uses this environment variable to figure out where to look for executable files when we call them without specifying a directory. All those directories listed there are where the shell will look for programs. For example, when we call the Python 3 program, the shell checks each of the directories listed in the path variable in order. And when it finds a program called Python 3, it executes it. So, as we said, we can read the contents of these variables from Python. Let's use a Python script to check that out. So, to access the environment variables, we use the environ dictionary provided by the OS module. In this case, we're using a dictionary method that we haven't used before. The get method is a bit similar to how we've been accessing dictionary values up until now. The difference is what happens when the value isn't present. When we retrieve a value from a dictionary using the key, as in os.environ *fruit, and the key isn't present, we get an error. If we use the get method instead, we can specify what value should be returned if the key isn't present. In other words, the get method allows us to specify a default value when the key that we're looking for isn't in the dictionary. So, what we're asking Python to do is try to retrieve the value associated with the key, but if the key is not defined, return an empty string instead. We're doing this for 3 different variables: home, shell, and fruit. Let's run the script and see what happens. We got the values for home and shell, but not for fruit. Well, that's because that variable isn't defined in the current environment. To define it in a way that our script will be able to see it, we need to run this in our command line. So, we define the variable by just setting a value using the equal sign and leaving no spaces in between. Along with this, the export keyword tells the shell that we want the value we set to be seen by any commands that we call. Now, let's call our script again. Cool. This time, we got the value that we wanted. So, you now know how to get the value of any environment variables from your Python scripts. Coming up, we'll dive into how command lines tell us whether they've succeeded or failed. Up to now, we've seen how different programs can read from and write to standard I/O streams, and how the shell environment can influence the execution of a program. Yet another common way of providing information to our programs is through command line arguments. These are parameters that are passed to a program when it started. It's a super common practice to make our scripts receive certain values by command line arguments. It allows the code of the script to be generic while also letting us run it automatically without requiring any interactive user input. This means that these arguments are really useful for system administration tasks. That's because we can specify the information that we want our program to use before it even starts. This lets us create more and more automation. And you can't argue with that, although you could argue my humor isn't really that humorous. But what can I say? I'm a better coder than I am a comedian. Anyway, we can access these values using the argvlist in the sys module. Let's check this out by executing a very simple script that just prints this value. First, let's use our friendly cat command to look at what the script does. As you can see, our script just imports the sys module and prints the sys.argvlist. Now, let's see what happens when we call the program. In this case, we called the script without any parameters. The list contains one single element, the name of the program that we just executed. Let's try passing a few parameters. Now, we see that each of the parameters that we pass is included as a separate element in the list. And last up, we have the concept of exit status, or return code, which provides another source of information between the shell and the programs that get executed inside of it. The exit status is a value returned by a program to the shell. In all Unix-like operating systems, the exit status of a process is 0 when the process succeeds, and different than 0 if it fails. The actual number returned gives additional info on what kind of error the program encountered. Knowing if a command finished successfully or not is helpful information, which can be used by a program that's calling a command. For example, it can use the information to retry the command if it failed. To check the exit status of a program, we can use a special variable that lets us see what the exit status of the last executed command was. The variable is the question mark variable, so to see the contents, we use $?. Let's try this out using the wc command, which counts the number of lines, words, and characters in a file. First, we'll pass it our variables.py script and check the exit value. So here, we first ran the wc command and it printed the values of lines, words, and characters for our Python script. Then, we printed the contents of the $question mark variable and we can see that the exit value was 0. That's because wc ran successfully. Here, wc couldn't run for the file that we passed because it doesn't exist. The command printed an error, and when printing the contents of the $question mark variable, we see that it finished with an exit value of 1. So, That's for system commands. But what about Python scripts? When a Python script finishes successfully, it exits with an exit value of 0. When it finishes with an error, like type error or value error, it exits with a different value than 0. We can make it exit with whatever value is relevant. Let's check out an example of this. This script receives a file name as a command line argument. It first checks whether the file name exists or not. When the file doesn't exist, it creates it by writing a line to it. When the file exists, our script prints an error message and exits with an exit value of 1. To try this out, let's first execute the script and pass a file that doesn't exist. Nice. Looks like that was successful. Check out how it exited with the exit code 0, even though we didn't specify this in the code. That's because that's the default behavior. Let's look at the contents of the file to make sure it's got what it should. Okay, and what do you think will happen if we now run the command again? You guessed it, we get an error because the file already exists. And so we get an exit code of 1. So we've now seen how we can pass command line arguments to our Python programs and how we can make our programs tell us whether they've finished successfully or not. These are both important tools that we'll use when creating automation. We'll use command line parameters to tell our programs what we want them to do without having to interact with them. And we'll use exit values to know if our command succeeded or failed, and then log failures and automatically retry the commands if we need to. Whoa, we've definitely learned a lot over these last few videos. Chances are it got a little tricky at some points, but you're doing an awesome job not letting these complex concepts stop you. Since you made it this far, you're bound to master all the ways that we can make our code interact with our shell environment. As always, take your time to review, and then head on over to the quiz to put your new knowledge to practice. Welcome back. We hope you're feeling good about streams, arguments, and exits. Now, we're going to submerge ourselves in sub-processes. So, let's dive in. Up to now, we've been using Python to interact with the operating system through baked-in functionality. For example, we've used file objects to read the contents of files, used the shutil module to check if the disk is full, and used the sys module to process standard input, get parameters, or generate an exit code. But what if we needed to run a system program from a Python script? Say, for example, that as part of a Python script, we needed to send ICMP packets to a host to check if it's responding. We could try to look for an external module that provides this functionality. Or we can just run the ping command, which will send packets for us. Sometimes it's easier or faster to use a system command as part of our Python script to accomplish a task, or use some functionality that doesn't exist in the Python modules, neither built-in or external. For these cases, Python provides a way to execute system commands in our scripts using functions provided by the sub-process module. Let's check out an example. First, we'll import the sub-process module, and then we'll call the date command, which shows the current date using the subprocess.run function. The run function returns an object of the completed process type. This object includes information related to the execution of the command. From the information that got printed, we can see that the return code of the command was 0. To run the external command, a secondary environment is created for the child process or subprocess where the command is executed. While the parent process, which is our script, is waiting on the subprocess to finish, it's blocked, which means that the parent can't do any work until the child finishes. And I bet a lot of parents out there are saying, I know that's right. After the external command completes its work, the child process exits and the flow of control returns to the parent. Then the script can continue its normal execution. Let's see this in action by calling the sleep command, which waits for a number of seconds that we tell it before returning. You may have noticed that while the sleep command was running, the interpreter was blocked and we couldn't interact with it. That's exactly what we mean about the parent process being blocked until the child process is done. Check out how we called the command. The run function receives a list that starts with the name of the command that we want to call, followed by any other parameters that we want to pass to that command. So, any elements following the program name are the command line arguments for it. In this case, we're requesting sleep to wait for 2 seconds. In the last two examples, the commands executed successfully, and so the return code inside the completed process instance was 0. Let's check out an example where the exit status isn't 0. If we call ls with a file name that doesn't exist, ls will print an error and return an exit status different than 0. This will be stored in the return code attribute of the completed process instance, and we can access that value in our code. We can see that the command failed and the return code stored was 2, letting us know that there was an error. We could use this information in the script to do something different in case of failure. Using the run function like this is useful if we just want to run a command and only care about whether or not it was successful. The output of the command will be printed to the screen, which means that our script has no control over it. This can be handy for system commands that either don't have useful output, like cp, chmod, sleep, and many others, or when we don't care about processing that output any further. In other words, when it's just fine to have the output printed to the screen. For example, if we're writing a script that's changing the permissions of a bunch of files in a tree of directories, we don't care about the output of the chmod command. We only want to know if it was successful or not. If instead we want to capture the output of an external command and then operate with the results, we need a different strategy. We'll dive into that in the next video. I'll see you there. If we want our Python script to manipulate the output of system command that we're executing, we need to tell the run function to capture it for us. This might be helpful when we need to extract information from a command and then use it for something else in our script. For example, say you wanted to create some stats on which users are logged into a server throughout the day. You could do this with a script that calls the who command, which prints the users currently logged into a computer. The script could parse the output of the command, storing the list of logged in users once per hour, and at the end of the day to generate a daily report. To be able to process the output of commands, we'll set a parameter called captureOutput to true when calling the run function. For our next example, we'll call the host command, which can convert a host name to an IP address and vice versa. When calling it, we'll pass the captureOutput equals true parameter and store the result in a variable so that we can access it. Let's give it a try. We know that the result variable is a completed process instance that we can access. We can check the return code attribute like we did before. And we can also print and operate with the output generated by the command, which is stored in the stdout attribute. What's that B at the beginning of the string? Well, that B tells us that this string is not a proper string for Python. It's actually an array of bytes. An array of bytes? This is a complex subject, so listen closely. Data in computers is stored and transmitted in bytes, and each can represent up to 256 characters. But there are thousands of possible characters out there, used to write in various languages. Chinese, for example, requires over 10,000 different characters. To be able to write in those languages, several specifications called encodings have been created over time to indicate which sequences of bytes represent which characters. Nowadays, most people use UTF-8 encoding, which is part of the Unicode standard that lists all the possible characters that can be represented. So, going back to our example, when we execute the command using run, Python doesn't know which encoding to use to process the output of the command. So, it simply represents it as a series of bytes. If we want this to become a proper string, we can call the decode method. This method applies an encoding to transform the bytes into a string. By default, it uses a UTF-8 encoding, which is what we want. So, with all that said, let's transform our array of bytes into a string and then split it into several pieces. In this way, we're operating with the output of the command that we ran, and we can do whatever we need to do with it. For example, we can choose to keep the last element of the list, which is the name that corresponds to the IP that we're looking for. Great, so we just looked at the captured standard output, but what about standard error? If we use the capture output parameter and the command writes any output to standard error, it'll be stored in the std_err attribute of the completed process instance. Let's look at an example of this. We'll try executing the rm command, which we use for removing files, passing a file name that doesn't exist. Let's check the return code of the command. Okay, it failed, just like we expected. Now, let's check the contents of the stdout and stderr attributes. So, we see that, in this case, the standard output was empty, but there was an error printed to standard error which we can access through the stderr attribute. This is a great example of how standard output and standard error are actually different streams, and so Python captures them separately. Okay, we've now seen that we can execute system commands from Python and check whether they succeeded or failed. We've also seen how to capture their standard output and standard error streams so we can use their content in our scripts. These skills can be super useful when writing scripts that use system commands for some involved tasks and letting our Python scripts cover a broader range of tasks. In the next video, we'll wrap up our discussion on subprocess module by learning some more advanced things that we can do when calling external commands. Alright, so we've seen how to run system commands from Python, how to check the exit value, and how to manipulate the normal output and error output of a command. The subprocess module offers a lot of extra options that we can use in our scripts. For example, we called out in an earlier video that one way of providing information to our processes is to modify the environment variables. Using this mechanism, we can change where the process looks for executable files, which commands it uses to interact with some parts of the system, the kind of output it'll generate, and a bunch more things. The usual strategy for modifying the environment of a child process is to first copy the environment seen by our process, do any necessary changes, and then pass that as the environment that the child process will see. Let's take a look at this. So, in this code, we start by calling the copy method of the OS environ dictionary that contains the current environment variables. This creates a new dictionary that we can change as needed without modifying the original environment. The change that we're doing in this script is adding one extra directory to the path variable. Remember, the path variable indicates where the operating system will look for the executable programs. By adding one entry to the path, we're telling the OS to look for programs in an additional location. To create the new value, we're calling the join method on the OS path sep string. This joins the elements of the list that we're passing with a path separator corresponding to the current operating system. So here, we're joining /opt/myapp and the old value of the path variable to the path separator. Finally, we call the myapp command, setting the end parameter to the new environment that we've just prepared. So, to recap, this script is modifying the contents of the path environment variable by adding a directory to it. We then call the myapp command with that modified variable. Doing it this way, the command will run in the modified environment with the updated value of path. There are a bunch more options that we can use with the run function. For example, we can use the cwd parameter to change the current working directory where the command will be executed. This can be really helpful when working with a set of directories where you need to run a command on each of them. We could also set the timeout parameter. This would cause the run function to kill the process if it takes longer than a given number of seconds to finish. This might be useful if you're running a command that you know might get stuck. For example, if it's trying to connect to a network and your computer is offline. Or we can also set the shell parameter. If we set this to true, Python will first execute an instance of the default system shell and then run the given command inside of it. This means our command line could include variable expansions and other shell operations. Without the shell parameter, this would not be possible. We'll learn more about the things that we can do with the shell later in this course. For now, just keep in mind that if you need to expand variables or globs, you'll need to set this parameter. But using this can be a security risk, so make sure you actually need it and be careful when using it if you do. Before we finish our discussion of the subprocess module, a word of caution. Interfacing with the underlying system directly in your Python scripts via subprocesses and system commands can be useful, especially if you need to do a specific task quickly, but it comes with some drawbacks. Using these system-level commands builds assumptions into our scripts about the infrastructure our automation will run on. And if those assumptions change, it can lead to unexpected effects or failures. These kinds of assumptions can change in multiple ways. What would happen to our automation if the flags for a terminal command change and our script continues to use the old flags? What happens if we switch operating systems from Linux to Windows? Will our scripts fail outright, or will they succeed in unintended and possibly harmful ways? Any change to the system or external commands our scripts use increases the chances of something breaking. Sometimes that break might be obvious, and other times it might be difficult to detect. If we're automating a one-off, well-defined task where developing a solution quickly is the biggest requirement, then using system commands and subprocesses can help a lot. But if we're doing something more complex or long-running, it's usually a good idea to use the baked-in or external modules that Python provides. So, before deciding to use the subprocesses, it's a good idea to check the standard library or PyPy repository to see if we can do the task with native Python, and to check if someone has already created the automation that we wanted to write. Remember that we never want to reinvent the wheel. How's this all sounding? That was a lot of info about advanced subprocesses, and it may take a little time for it to all, well, sink in. Now it's a good time to use your local Python installation and try out some functions and commands that we saw. Check out the cheat sheet in the next reading, which sums up how to use the subprocess module. See if you can come up with other ideas and other things that you can do with the system commands and try those out. Once you feel ready to take the plunge, there's a quick quiz waiting for you after that. Whoa, you're on a roll working through these new techniques. So far, we've learned a bunch of new concepts that let us interact with the system. We've learned how to read and write files, how to use regular expressions to process them, how to interact with the system shell, and how to execute commands in that environment. That's really impressive, so take a quick moment to think about how far you've come and about all the new cool stuff you'll be able to do by interacting with the system. Now, we're going to take a look at how we can use these tools to help us with our day-to-day work. In the next few videos, we'll dive into a concrete example centered around processing chunks of data, the kind of data you might find in a syslog file or a web request log. The different events that happen in programs that are running in a system and aren't connected to a terminal are usually written to log files. Log files contain a lot of useful information, particularly when you're trying to debug a tricky problem that's happening on a computer. On the flip side, sometimes it can be overwhelming to try to find something inside of a log file that contains a whole lot of lines with a whole lot of things in them. So it's a good idea to learn how we can process these files and get our tools to extract information that we want out of them. To do this, we'll go back to our knowledge of regular expressions. Using regexes in our scripts gives us a great deal of flexibility when processing log files and other text data sources too. In a script, we can program any kind of behavior we want, so we can manipulate and process text data and get results we need. We're going to show you how you can do this in the next couple of videos. All right, let's get started. When working with log files in a script, our first step is usually to open them so our code can access their contents. We've discussed various methods of operating on files. The usual technique is to call the open function, which returns a file object, and then iterate through each of its lines using a for loop. For example, to open a file received as a parameter of our script, we can use code like this one. Remember that, for performance reasons, when files are large, it's generally a good practice to read them line by line instead of loading their entire contents into memory. For our example, let's say the log file contains these messages. The server that generates this log file has been acting strangely, and we suspect it's due to a cron job started by one of the system administrators. You might remember that cron jobs are used to schedule scripts on Unix-based operating systems. To find out what's happening with the server, we want to audit the log files and see exactly who's been launching cron jobs. By looking at the sample log, we can see that the lines that will be most interesting to us are the ones that contain the cron substring. These lines also show the user who started the cron job wrapped in parentheses. With this info, we can ignore any line without the cron substring in it. We can check for this using the in keyword. Here, we're using the continue keyword, which tells our loop to go to the next element. So, if the line doesn't contain the string that we're looking for, we'll skip it and go to the next line. Once we know we're processing the right log line, we can use our knowledge of regular expressions to extract the username. We can do this in a bunch of different ways. In this example, we'll use escape characters, capture groups, and the end of string anchor. Before we add the expression to our script, we'll construct it and test it out in an interpreter. Let's take a closer look at this expression. Since the username is found at the end of the log line, we use the $ anchor to only match text that is at the end of the line. To find the username, we look for the word user followed by a string wrapped in parentheses, as that's how these lines are structured. This means that we need to escape those parentheses with a backslash. And since we want to extract the actual username, we use another couple of parentheses to create a capturing group. And for the username itself, we're matching any alphanumeric characters by using \W+. With that cleared out, let's test it out with a sample line. Tisk tisk, looks like we've got a naughty user. On the plus side, it seems that our regular expression works correctly. We can now use the expression in our code. Let's add it to our script. Okay, our script should be able to process the log file that we showed earlier. Let's save it, make it executable, and run it, passing the example syslog file that we showed. Our script is shaping up nicely. We've located each user that started a cron job in our log file and printed them to the screen. Pretty nice, right? We took a few steps to craft this script. If any of these steps were unclear, review the video and practice on your own until you get it. Up next, we'll do a bit more processing with those results. In the last video, we wrote a script that processed a log file and extracted the names of each user who had started a cron job in the machine that we were investigating. This can be really helpful, but there's more information that we might need. To improve our output, it would be a good idea to have a count of how many times each username appears in our log. Can you think of what we can use to do that? If you guessed a dictionary, then you're right. As we've seen in earlier examples, dictionaries are a great structure to use when we want to count appearances of strings. We'll store the username as the keys of a dictionary, and we'll use the value to count the number of times that each username appears in the file. To do this in fewer lines, we'll use the get method that we saw earlier in another video. Let's try it out in the interpreter before adding it to our code. First, we'll create an empty dictionary using curly brackets. Then, we'll set the variable name as GoodUser, for example. And now, we'll set the value associated with the key as one more than the current value, and we'll use the get method to get the current value, like this. Again, we're taking the current value in the dictionary, but passing a default value of 0, so that when the key isn't present in the dictionary, we get a default value. We then add 1 and set it as a new value associated with that key. Let's check out the current contents of the dictionary. Great. And what happens if we do the same operation again? Fantastic. We see that this operation works successfully both when the key is already in the dictionary and when it isn't. Now, let's add this to our script. We'll need to initialize the empty dictionary at the beginning of our code. And before we add any values to the dictionary, we want to check that we actually got a match to our regular expression. Do you remember how we can do that? We can check if the result variable is none. We'll use that same technique as before, and use the continue keyword if the result is none. Okay, we can now add the values to the dictionary as we process the file instead of printing them. To do that, we'll define a name variable that will store the captured group. And then we'll use that one as a key for our dictionary. And finally, let's print the resulting dictionary once we're done going through the file. Nice. Our modified script is ready. Let's try it out with our test file. Cool. Our script now allows us to very quickly see who's been starting cron jobs on the server and at what frequency. Now, we can use the information to investigate the issue more deeply. It's pretty cool to see how all these different ways of managing data and processes come together in a real-world example, isn't it? Nice job. Hopefully, these examples are helping you see how your Python programming skills can help you quickly get the information that you want when you're debugging a problem. We'll keep expanding on this topic in this and later courses. Up next, a quiz to let you put all this new knowledge to work. Wow, this has been quite a ride. You should be super proud of yourself for making it all the way here. Over the course of the module, we've learned a bunch of different ways that we can provide information to our scripts, like reading from standard input, the environment variables, and command line arguments. And we've discovered how our scripts can provide data to our environment by printing the standard output or standard error, or by using different exit values. We also looked at how and why we can execute system commands from Python using the subprocess module. And we ended our journey by checking out a concrete example of using Python to process yet another source of information, log files. It's normal for this to seem a bit abstract right now, since we've been talking mostly about concepts. but you can probably think of some examples of things that you could do with them. It's pretty fun to come up with new and creative ways to apply these tools to your day-to-day activities. Next, you can put all this knowledge into practice with the upcoming lab. There, you'll need to use your newly acquired system programming skills to solve real-world problems related to log files. Remember that you can use the cheat sheets that we've given you whenever you need to quickly look something up. You can always rewatch the videos as many times as you need. Best of luck, and remember, you've got this. Welcome back, and a big congratulations for making it this far. The concepts that we're covering are definitely not easy. By staying on track, you're not only expanding your programming horizons, but also showing that you have what it takes to make it in the IT field. Over the course of the past modules, we've been learning all the things that we can do with Python, from managing files to processing text, starting system processes, and a whole lot more. Up to now, whenever we wrote Python code, either in the interpreter or in our scripts, we've been testing it by manually running it and seeing if it did what we expected it to do. Buckle up, because that's about to change. In this module, we'll dive into how we can create automatic tests that will perform these kinds of checks for us. This lets us concentrate on just writing the code instead of checking if any changes that we make to it break the previous functionality. It would also help us verify that features we add do what we expect in lots of possible ways. We'll learn about the different kinds of testing that are out there and how we can use them to make our code more reliable. And finally, we'll also learn about how to handle errors and exceptions in Python code, how to trap those errors so they don't stop our programs from completing, how to raise errors when necessary, and how to test our code generates the right kinds of errors. That sounds interesting, right? Now, let's get to it. When you're writing a very simple piece of code, say for example that you're adding two variables, it's pretty straightforward to know what the code does and be sure that it does it correctly. As the operations become more complex, using loops, conditionals, calling more and more functions, it's harder to really be confident that the code will do what it's supposed to. This is where software testing comes into play. Software testing is a process of evaluating computer code to determine whether or not it does what you expect it to do. When you test a piece of software, you want to find the errors and defects and see where things go wrong. Software testing is similar in lots of ways to the tests performed in the manufacturing process of a new piece of machinery. When a new car comes off the line, you want to make sure that when you press the gas, the car will go, and when you press the brakes, the car will stop. It's the same idea with software. You want to make sure that when you run a program, it behaves the way that it should. Then you can really put the pedal to the metal. Vroom vroom. Scripts and programs can fail in all sorts of strange ways, especially as they become more and more complicated. In all but the most simple programs, it's next to impossible to test for everything that could go wrong. Even though this means that a certain number of bugs might exist in your scripts without you realizing it, don't worry. Writing tests can help you eliminate a whole bunch of bugs, helping to improve the reliability and the quality of automation. Tests can help make good code great. The field of software testing is pretty broad. In the next few videos, we'll explore some fundamental concepts involved like automated testing, unit tests, integration tests, and test-driven development. As with lots of topics covered in this course, we'll do a quick rundown of the many concepts around testing. It won't be enough instruction for you to become a testing expert, but it should help you with automatically testing your scripts. Up next, we'll talk about the differences between manual and automated testing. So, let's shift gears and get started. One of the tasks that programmers have to do when writing code is test it to make sure that it behaves the way that they expect it to. Having good tests for our software can help us catch mistakes, errors, and bugs before we deploy our scripts to perform real-world automation tasks. The most basic way of testing a script is to run it with different parameters and see if it returns the expected values. We've done this kind of manual testing for some of the code that we've written in this course already. Executing a script with different command line arguments to see how its behavior changed is an example of manual testing. Using the interpreter to try our code before putting it in a script is another form of manual testing. Formal software testing takes this process a step further, codifying tests into its own software and code that can be run to verify that our programs do what we expect them to do. This is called automatic testing. The goal of automatic testing is to automate the process of checking if the returned value matches the expectations. Instead of us humans running a function over and over with different parameters and checking that the results are what we expected them to be, we let the computer do this for us. Automatic testing means we'll write code to do the test. Why would you write more code to test the code you have? Because when you're testing your code, you want to check if it does what it's supposed to do for a lot of different values. You want to verify that it behaves the way you expect it to with as many possible values, known as test cases. Say you're writing a script that updates a list of email addresses to use a new domain, similar to the one we wrote a while back. You'll want to test what happens when your list of emails has 1 element, 2 elements, or 10 elements. You'll want to test what happens if the new domain is 1 character long or 20 characters long, or even an empty string. You'll also want to test what happens if the list contains only emails that need to be updated, only emails that don't need to be updated, or a mix of them. As you can see, the list of things that you want to test for can get very long, very fast. The more test cases that you include in your test, the better tested your code is, and the more you can guarantee that your code does what you expect it to do. If we're testing this manually, it's unlikely that we'll go through all the cases whenever we change our code. We'll test just a few, possibly letting a bug slip through. Not ideal. This is why we don't want to perform these tests manually, and instead, we want to make our computer do it for us. Just like with any example of automation, the advantage of automatic tests is that we can run them as many times as necessary and will always get the same results. The computer will do the same checks over and over and will always make sure that the return value matches our expectation. When, for some reason, the results don't match the expectations, the code will raise an error so that we can check the code and find out what's going on. There's a bunch of different types of tests that we can write to perform automatic testing. The one that we're going to concentrate on in the next few videos is called unit testing. Once we've covered unit testing, we'll talk about other kinds of testing and when to use each. But before that, let's check that we're on track. Doesn't all this talk about testing make you want to take a quick quiz? As we mentioned, there are lots of different types of tests that we can write to perform automatic testing. The most common type is a unit test. Unit tests are used to verify that small, isolated parts of a program are correct. Unit tests are generally written alongside the code to test the behavior of individual pieces, or units, like functions or methods. Unit tests help assure the developer that each piece of code does what it's meant to do. An important characteristic of a unit test is isolation. Unit tests should only test the unit of code they target, the function or method that's being tested. This ensures that any success or failure of the test is caused by the behavior of the unit in question and doesn't result from some external factor, like the network being down or a database server being unresponsive. In other words, when testing a function or method, we want to make sure that we're focusing on checking that the code in that function or method behaves correctly. We don't want our test to fail for external reasons. On a related note, our test should never modify the production environment. This is a live environment that runs the software that users interact with. When developing tests, if for any reason we do need to interact with some other software, we'll normally do that in a test environment, where we'll have control over how it behaves. It's our house, our rules. So, the goal of the unit test is to verify that small, isolated parts of a program are correct. How do we do that? It generally boils down to a simple pattern. Given a known input, does the output of our code match our expectations? Let's take a piece of code similar to what we wrote a while back to rearrange a name in the format last name, comma, first name. And think about how we test it. How do you think we can test that it works the way you expect it to? Let's start by manually validating that for a given input, it produces the expected result. We'll check this by importing the function in an interpreter. To do that, we'll use a keyword that we haven't seen before, from, like this. In this case, rearrange is the name of the module that contains the rearrange name function. By importing it in this way, we can call the function without having to write the module name each time we want to call it, like this. The function has produced the output we expected given the input we provided, and so it has passed this particular unit test. Gold star, hang it on the fridge. The test focused on a small, isolated piece of the code and validated our assumption about how it worked. Because the scope of the test is restricted to a small, specific unit, these types of tests usually run pretty quickly, and debugging them is simple, since there are a limited number of reasons for them to fail. Creating unit tests for our code will mean writing a bunch of test cases that verify that when we input some parameters, we get the output that we want. Of course, the whole point is to run these tests automatically, so that we don't have to manually do this ourselves each time. Up next, we'll talk about how we can actually write automatic tests in Python. Exciting, right? We've now looked at the principles behind automatic testing. We know that by having automatic tests, we can run them as many times as necessary to make sure that our code does what we want it to do. So, how do we do this in Python? We need to write some code that runs the test and verifies the output. This way, we can get our computer to do the work for us. To demonstrate the testing workflow, we'll create unit tests for the rearrange name function from the previous video. As we touched on earlier, automatic tests are usually written alongside the code that we want to test. What this means in practice is creating a separate Python file with the test. The convention is to call this script with the same name of the module that it's testing and appending the suffix _test. So, for our rearrange module, we'll create the rearrange test.py file. We'll test the rearrange name function of the rearrange module. So let's import that function the way we did before in the interpreter. Okay, we're ready to start writing the test. To help us with that, Python provides a module called unit test. Thanks, Python. This module includes a number of classes and methods that let us easily create unit tests for our code. The first thing we'll do is import the unit test module we'll need for testing. The unit test module provides a test case class with a bunch of testing methods ready to use. To access this functionality, we create our own class that inherits from test case, thus inheriting all those testing methods. So we're going to write our own test rearrange class that inherits from test case. Do you remember what the syntax for that was? We need to include the class that we want to inherit from in the parentheses. We've called our test class test rearrange and indicated that it should inherit functionality from the test case class located in the unit test module. Any methods we define in our test rearrange class that start with the prefix test will automatically become tests that can be run by the testing framework. So we're ready to write our first test case. What's it going to be? In our last video, we manually tested one simple case. Let's turn that manual test into an automatic test that verifies the basic names are formatted correctly. With this method, which we've called test basic, we kick off by setting up our expected inputs and outputs. We then use the assert equal method provided to us by the test case class we inherited from to verify that what we expected is exactly what we got. The assert equal method basically says both of my arguments are equal. If that statement's true, then the test passes. If it's false, the test fails and an error is printed to the screen when the test is run. Okay, we've got our first unit test. So how can we run it? In the main part of our program, we'll call the unittest.main function, which will run the test for us. All right, we're ready to run the test. We'll do that by executing the file that we just created. Let's make our script executable and then run it. Looks good. The output is pretty descriptive, printing out some information about how long our group of tests, or test suite, took to run, as well as the number of tests and whether or not they passed. Just like that, we've tested our first function. It's pretty cool, right? I know there was a lot going on here. If the code is confusing, complex, or didn't really sink in yet, that's okay. Take the time to practice on your own and review the content until it feels natural. Coming up, we'll test even more cases. By now, we know how to write automatic tests in Python. Our test suite includes only one test case though. We need to make it grow. Choosing test cases can be an exercise in creativity. Coming up with different ways a piece of code might break can actually be super fun. We'll usually test that our code works in the general case. But we should also see what happens when we give it some input that we may not expect it to run into under normal operations. For example, what would happen in our function if we gave it an empty string? Let's add a test for that and see. In this case, we're testing for an empty input string. We're saying that we expect our function to return an empty string when it receives an empty string. We check this behavior by using the assert equal function. All right, let's run this. Oh look, our test failed. We caught a problem with our code. Let's take a closer look at the information that the failure gives us. After all, that's what errors are for, right? This error tells us that the test called testEmpty failed, and we see that it failed with a type error, saying that none is not subscriptable. Interesting, we've just discovered an edge case. Edge cases are inputs to our code that produce unexpected results, and are found at the extreme ends of the ranges of input we imagine our programs will typically work with. Edge cases usually need special handling in scripts in order for the code to continue to behave correctly. In our rearranging example, we can handle this edge case by performing a simple check of the result variable before operating with it. With this change, if we use our function with normal input, we'll still get a result that we got before. If we try to use an empty string, we'll catch it with our check and return the original empty string instead. Whether or not we handle this kind of error depends on how we want the scripts to behave. In our specific case, returning the original value makes sense when we can't rearrange it. But sometimes, you might actually want your program to crash with an error rather than to go on as if nothing happened. Remember that it's bad for automation to fail silently. Other kinds of edge cases usually include things like passing 0 to a function that expects a number, or negative numbers or extremely large numbers. These types of conditions are good to consider when writing your test, since they can cause your code to crash or behave in unexpected ways. Sometimes it pays to be a pessimist. You can see how it might require some creativity to come up with these examples. The upside is that when writing automatic tests, once you've come up with an example, it's there to stay. So, now that we've fixed our code to behave correctly with this edge case, let's run our test suite again and see if the problem is fixed. Yes, our tests pass. We fixed a bug in our code, and by adding an automatic test, we can make sure that it won't happen again. Can you think of other test cases that we might want to add to our test suite? We'll look into a couple more in the next video. Up to now, we've added a basic case and an edge case to our test suite. When we added the edge case, it caused our function to generate an error because we didn't handle this correctly. And so we fixed it by changing our function. Can you think of some more examples that will make our function misbehave? Remember, when we first wrote the function, we came across names with spaces or dots that will make our regular expression not match. We fixed that already, but it's still a good idea to add a test case to make sure that our code still works how we expect it to. In this case, we're testing that someone with more than one given name still gets their name properly rearranged. Let's run our test suite and see if it passes or not. Alright, we now have 3 tests and all of them pass. To find more bugs, we need to exercise our creative muscles and think of other examples that might cause our code to fail. How about someone who has only one name? In this case, this person only has one name, so there's no comma in our string. We expect the result to be the same name we provided to the function. Will that work? Let's check and find out. Whoops, this one failed. Bad news for Voltaire. The test output in this case looks slightly different than before. It shows the name of the test that failed, which is test1 name. But now, instead of giving us a type error, we see an assertion error, which means the original and expected values don't match. It looks like our function returned an empty string instead of the original name. That's because there's a bug in our code. And what do we do when we have a bug in our code? We squash it. When we checked if the result was none, we returned an empty string, which made our previous test pass. What's happening now is that we're passing a name that doesn't include a comma, which makes our result variable none, and so the function is returning an empty string. The fix for this is pretty simple. Instead of returning an empty string when the result is none, we'll return the original name variable. So that should be enough, right? Let's save our changes and run the test suite again. Bingo! We fixed all the bugs and all our tests pass. One of the great things about running tests in a suite like this is that we now know that all the test cases we wrote were handled correctly. Our code works for basic names, empty strings, double names, and single names. If we found another case that made our test break, we could add it to the suite, fix the bug, and then run the whole suite again, being assured that all the other cases are still working. You should take a moment and reflect on what you've already learned in this module. It's super impressive, and it's going to fit nicely into your IT toolkit. Coming up, a cheat sheet includes all the syntax we've been seeing about writing unit tests, plus pointers for more information that you might find useful. After that, you'll have a chance to write some interesting tests yourself. There are lots of different tests that we can use to make sure our software is behaving how we expect it to. We've explored unit tests in detail, which are both simple to write and a very powerful way to catch bugs. But there's a lot more to software testing. One interesting concept is whether our test is a white box test or a black box test. White box testing, also sometimes called clear box or transparent testing, relies on the test creator's knowledge of the software being tested to construct the test cases. With a white box test, the test creator knows how the code works and can write test cases that use the understanding to make sure that everything is performing the way it's expected to. On the other hand, in black box testing, the software being tested is treated like an opaque box. In other words, the tester doesn't know the internals of how the software works. Black box tests are written with an awareness of what the program is supposed to do, its requirements or specifications, but not how it does it. For example, a simple black box test could be to verify that when you type www.google.de in your browser, the Google search page for Germany is returned. You might not know how Google servers process your request, but you know what the end result should be. Both white box and black box tests have their own advantages. White box tests are helpful because the test writer can use their knowledge of the source code to create tests that cover most of the ways that the program behaves. Black box tests are useful because they don't rely on the knowledge of how the system works. This means their test cases are less likely to be biased by the code. They usually cover situations not anticipated by the programmer who originally wrote the script. Not all tests that we write need to fall into one category or the other. We can write unit tests that are either white or black box, depending on which testing methodology is chosen. If the unit tests are created before any code is written, based on specifications of what the code is supposed to do, they can be considered black box unit tests. If unit tests are written alongside or after the code has been developed, the test cases are made with a knowledge of how the software works. They are white box tests. One way isn't strictly better than the other, since each gives you a different path to make your code more reliable. Not everything is so black and white, or as we'd say in the coding world, binary. As an IT specialist, you might need to test that software written by others behaves the way you expect it to. To do this, you can use a combination of black box and white box test. Let's say that you have an online catalog of products that are sold by your company. You could have a black box test that verifies that the details for a product are displayed when you open the page for a specific product. Apart from that, you could have white box tests that calls the different functions used by that page, checking that the prices are displayed in the right currency, that the description is correctly wrapped, and so on. Next up, we'll talk about other kinds of testing beyond unit tests and what roles they play in improving the quality and reliability of your scripts. When we looked at unit tests, we called out that they should focus on one specific unit, a function or method that's being tested. This allows the test to verify that the unit provides expected functionality regardless of the rest of the environment. On the other hand, integration tests verify that the interactions between the different pieces of code in integrated environments are working the way we expect them to. While unit tests shouldn't cross boundaries to do things like make a network request or integrate with an API or database, the goal of an integration test is to verify these kinds of interactions and make sure the whole system works how you expect it to. Integration tests usually take the individual modules of code that unit tests verify, then combine them into a group to test. Depending on what our program does and how it interacts with the rest of the systems involved, we might need to create a separate test environment for our test, which runs a test version of the software that we're trying to verify. We might be able to run our tests against the actual version of our system that's running, but That's only if our code doesn't make any changes to the production environment. Whenever your company is deploying a system that's somewhat complex, having integration tests will help make sure that all the pieces come together the way you expect them to. These tests usually take a bit more work to set up because you'll need to make sure that you have the test versions of all relevant systems. But they might help catch issues that unit tests won't detect, so the extra effort is definitely worth it. For example, if the service you're trying to test interacts with a database, you'll want to set up a separate test database with a test user and test tables. This lets you run all tests you need in an environment that you can control without risking modifying the production database. A variant of unit tests are regression tests. They're usually written as part of a debugging and troubleshooting process to verify that an issue or error has been fixed once it's been identified. Say our script has a bug and we're trying to fix it. A good approach to doing this would be to first write a test that fails by triggering the buggy behavior, then fix the bug so that the test passes. Regression tests are a useful part of a test suite because they ensure that the same mistake doesn't happen twice. The same bug can't be reintroduced into the code because introducing it will cause a regression test to fail. Smoke tests, sometimes called build verification tests, get their name from a concept that comes from testing hardware equipment. Plug in the given piece of hardware and see if smoke starts coming out of it. When writing software, smoke tests serve as a kind of sanity check to find major bugs in a program. Smoke tests answer basic questions like, does the program run? These tests are usually run before more refined testing takes place, since if the software fails the smoke test, you can be pretty sure none of the other tests will pass either. As they say, where there's smoke, there's fire. For a web service, a smoke test will be to check if there's a service running on the corresponding port. For an automation script, the smoke test would be to run it manually with some basic input and check that the script finishes successfully. Other types of tests are load tests. These tests verify that the system behaves well when it's under significant load. To actually perform these tests, we'll need to generate traffic to our application simulating typical usage of the service. These tests can be super helpful when deploying new versions of our applications to verify that performance doesn't degrade. For example, we might want to measure the response time of our website while there are 100 requests per second on our pages, or 1,000, or 10,000. The actual numbers will depend on the expectations of how much traffic our website will receive. Taken together, a group of tests of one or many kinds is commonly referred to as a test suite. A good diversity of test types can create a more robust test suite that helps ensure your scripts and automation do what you tell them to. There are many more kinds of tests out there. We've only touched on a few of the most common types. If you're interested in learning more about the ways software can break and how to test for that, all kinds of books and articles have been written on the subject. Speaking of tests, we have a huge and difficult test coming up. Just kidding. Up next, we'll learn about a technique called test-driven development. You might expect that most testing happens after the code has been written. This seems like a natural progression. First, you write your script, then you write tests that verify that the script does what you want it to do. But this isn't always the best approach. A process called test-driven development, or TDD, calls for creating the test before writing the code. This might seem a bit counterintuitive, but it can make for more thoughtful, well-written programs. When presented with a new problem that can be solved by automation, your gut instinct might be to fire up your code editor and start writing. But creating some tests first makes sure that you've thought about the problem that you're trying to solve and some of the different approaches that you might use to accomplish it. Writing a test first also helps you think about the ways your program could fail and break, which can lead to some valuable insights and even change the approach you take for the better. The test-driven development cycle typically involves first writing a test, then running it to make sure it fails. After all, you haven't written the code to make it pass yet. Once you've verified it fails, you write the code that will satisfy the test, then run the test again. If it passes, you can continue on to the next part of your program. If it fails, you debug and run the test again. The cycle is repeated for each new feature of your script until it's up and running. So, before you write your next Python program, you might want to think about the kinds of tests you can create to make sure it's working as you expect. There are all kinds of resources out there if you'd like to learn more about how you can create code using the test-driven development approach. Lots of them are Python-centric, but the principles can be applied to any language you need to create in. Hopefully, you can see the benefits of writing tests to validate the code you write, and you've gained some understanding about the different testing techniques available. Remember that good tests help make any automation and scripts you write more robust, resilient, and less buggy. Having reliable automation makes life better for everyone. Many companies take testing a step further and combine it with their version control systems and development processes. When engineers submit their code, it's integrated into the main repository and tests are automatically run against it to spot bugs and errors in a process called continuous integration. Although useful, setting up a continuous integration process can be a big undertaking. We'll talk more about it in a later course. In the meantime, if you use unit tests to validate the code you write, you're already on your way to a more reliable and robust automation. Up next, a reading summing up all the different types of tests we mentioned, followed by a quick quiz to make sure you're on track. Along our journey learning Python, we've encountered errors generated by the interpreter a bunch of times. We've seen examples of type error, index error, value error, and others. Up to now, whenever the interpreter threw one of these at us, we changed our code to avoid the error. That's a common approach, since whenever the interpreter raises one of these errors, the program stops. And we don't want our scripts to come to an end before they're done doing their work. Sometimes it's easy to make a verification with the conditional to avoid the error, like in our earlier example of the rearrange name function where we checked if the result from our regular expression search was none and did something different in that case. Other times, there are so many things that could go wrong that checking for all of them becomes challenging. Say you had a function that opened a file and did some processing on it. What if the file doesn't exist? What if the user doesn't have permissions to read the file? Or what if the file is locked by a different process and can't be opened right now? We could check all of these conditions, but what if there's yet another thing that could cause the open function to raise an error? In a case like this, a better approach is to use the try except construct. Let's look at how it works in an example. Our character frequency function here reads the contents of a file to count the frequency of each character in them. To do that, the first step is to open the file. In this example, we've put the call to the open function inside a try except block. What this does is first try to do the operation that we want, which in this case is to open the file. If there's an error, it then goes into the except part of the block that matches the error and does whatever cleanup is necessary. Here, we have only one except block for the OS error type, but there could be more blocks if the functions called could raise other types of errors. So, when writing a try except block, the important thing to remember is that the code in the except block is only executed if one of the instructions in the try block raised an error of the matching type. In this case, in the except block, we're returning none to indicate to the calling code that the function wasn't able to do what was requested of it. Returning none when something fails is a common pattern, but not the only one. We could also decide to set a variable to some base value, like 0 for numbers, empty string for strings, empty list for list, and so on. It all depends on what our function does and what we need to get that work done. The important point is that when we have an operation that might raise an error, we want to handle that failure gracefully by using the try except block. The operation could be opening a file, converting a value to a different format, executing a system command, sending data over the network, or any other action that might fail and isn't trivial to check with a conditional. To use a try except block, we need to be aware of the errors that functions that we're calling might raise. This information is usually part of the documentation of the functions. Once we know this, we can put the operations that might raise errors as part of the try block and the actions to take when errors are raised as part of the corresponding except block. You're probably asking yourself, how do I raise my own errors? Lucky for you, that's up next. We'll dive into how to raise our own errors when necessary. In the last video, we looked into how to handle errors when they're raised by the functions that we call. In some cases, we might want to raise an error ourselves. This usually happens when some of the conditions necessary for our function to do its job properly aren't met, and returning none, or some other base value isn't good enough. Let's look at this through an example. Say we had a function that verifies whether a chosen username is valid. One of the checks this function does is verify that the provided name is at least a certain amount of characters, with the minimum value received by a parameter. Something like this. In this function, we're first checking that the username variable has at least min-leng characters. After checking that, we verify if there are any non-alphanumeric characters in the string, which is another criteria for validating a username. If all the checks pass, we return true to indicate that the username chosen is valid. This code works as long as the provided values are sensible. What would happen if the min-leng variable is 0 or a negative number? Our function will allow an empty username as valid, which doesn't make much sense. To prevent this from happening, we can add an extra check to our function, which will verify the received parameters are sane. In this case, returning false would be misleading, because it's not necessarily that the username is invalid, but the provided min-leng value doesn't make sense. So let's add a check to verify that min-leng is at least 1, and raise an error if that's not the case. Cool. As you can see, the keyword to generate an error in Python is raise. We can raise a bunch of different errors that come already pre-built with Python, or we can create our own if the standard ones aren't good enough. In this case, we're raising a value error, a type of error that we've come across before to indicate that there was a problem with one of the values of the parameters. Let's save our code and then try it out in the interpreter. Success! We imported our function and called it with an invalid parameter. Our function successfully raised an error, just like we wanted. I bet you didn't expect that there'd be a point where getting an error would mean you're doing things right, huh? Let's also try calling it with valid parameters to see if those work. Okay, that seems to work. What if instead of passing a string, we pass something different as a username to validate? Let's try a few examples. First, let's try a number. Uh-oh. In this case, the Python interpreter raised an error because our code is trying to use the length function and we can't do that with integers. Let's try passing a list, which does have a length function. First, an empty list. Because this list is shorter than the minimum length, our code returned false. Now, let's try it with a list of one element. So in this example, we got a different error because we were trying to use the isAllNum method, which is not available on list. We managed to get 3 different possible results when passing a value that wasn't a string. Depending on how our function is going to be used, this could be okay. It's usually the responsibility of whoever's calling a function to call it with the right parameters. But in some cases, we might want to do this explicitly by checking that we're receiving a value that makes sense to that function. So, let's look at an alternative to the raise keyword that we can use for situations when we want to check that our code behaves the way it should, particularly when we want to avoid situations that should never happen. This is the assert keyword. This keyword tries to verify that a conditional expression is true, and if it's false, it raises an assertion error with the indicated message. Let's add an assertion to our function. We've added an assertion that verifies that the type of the username variable is str, which we know is a name that the interpreter uses for strings. If the function is called with a username parameter that's not a string, an error will be raised with the message we provided. Let's try this out. First, we'll need to close our interpreter and restart it to import the modified module. Alright, let's try calling our function with something that's not a string. Aha! We see that our function now raises an error type assertion error if the first parameter isn't a string. As we've called out, we usually don't need to check the types of our parameters. Depending on what our function does, it might be perfectly okay for it to allow scripts to call it with parameters of different types. Assertions can be super helpful if we're debugging some code that's not behaving the way we expect it to. We can add them at any point where we want to ensure that the variables contain the values and types that they should, or when we think that something that shouldn't happen is happening. Heads up though, assertions will get removed from our code if we ask the interpreter to optimize it to run faster. So, as a rule, we should use raise to check for conditions that we expect to happen during normal execution of our code, and assert to verify situations that aren't expected but that might cause our code to misbehave. By now, we've seen how we can handle errors when the code we call generates them, and how we can raise our own errors when we want our code to signal that something hasn't gone well. This is complex stuff, and it's okay if it takes a little while for it to sink in. As usual, we'll include a cheat sheet and give you plenty of opportunities to practice your newly acquired error handling skills. Up next, we'll look into how we can add tests to verify that our function raises the errors that it needs to raise. In earlier videos, we looked into how we can create unit tests for our functions, for both the basic cases and the edge cases. We called out that we should try to cover lots of different possible cases, to make sure that our function behaves correctly in all of them. With some edge cases, like the negative value of minlen in our earlier example, the expectation is that the function will raise an error and we want to be able to test that too. So, how do we do that? Well, we use the assert raises method provided by the unit test module. Let's check this out by adding a couple of test cases to the test suite for our validate user function. This is the existing test suite. As you can see, we've got a few test cases checking that the function is working correctly when it receives sane parameters. We now want to add some other cases for when it receives parameters that don't make sense, like a negative value for minlen or a username that's a list instead of a string. Let's do that now. We can see that the assert raises method works a little bit differently than the assert equal method that we used before. In this case, we need to first pass the error that we expect the function to raise, then the function name, followed by any parameters that need to be passed to that function. Behind the scenes, this method is calling the function that we want to test using the try except block and checking that it does raise the error that we said it would raise. Okay, let's run this test suite and verify that our code works correctly. All clear. With that, you now know how to test your code to verify that it does what it should, and how to test that it raises the right error when that's what you expect. Coming up, a cheat sheet covering all the error handling syntax that we just saw in these videos, followed by another opportunity for you to test your skills. Congrats on making it through this module. Take a moment to reflect on how much you've learned and accomplished throughout this course. It's no small feat. You set up Python on your local environment and learned how to manage files, process text, start system processes, use regular expressions, and process log files. Over the past several videos, we did a rundown of the different approaches to testing and error handling that we can use in Python. We learned about the different types of tests and how to write our own unit tests in Python. Hopefully by now, you're beginning to see how automatic testing can play a significant role in keeping your code free of bugs and ready for a digital picnic. In the graded assessment for this module, you'll have the opportunity again to practice your skills through a real-world scenario where you'll need to solve a problem with some buggy code. But don't worry, you've got this. And if for any reason you get stuck, feel free to go back and rewatch the videos. And of course, practice, practice, and practice. I'll see you on the other side. Welcome back. And once again, congrats on making it this far. We're almost to the end of this course, and you're surely realizing how much your programming skills are improving. Can you see how these concepts are going to benefit you as you tackle tasks in your IT job? In this module, we'll broaden our exposure to what the Linux operating system has to offer. We'll do a rundown of the most common Linux commands, and we'll see how we can connect the input and output streams to files or even to other programs. We'll also dip our toes into scripting in a different programming language called Bash. You might be wondering, why are we learning a new programming language when I'm just getting comfortable with Python? Well, don't bash your head against the wall just yet. Being able to script in Bash can be a really useful complement to our Python scripts. Don't worry, it's going to be a bash. Okay, I'll stop with the bash puns for now. Anyway, imagine that you wanted to convert all image files in one directory from PNG to JPEG format. There's a command called convert that you can use to do this. You could definitely do this in Python by going through all the files in the directory using os listdir and calling convert using subprocess run. But it would end up being a really complex script for something that's actually super simple. You'll soon see how you can do this in Bash with just 3 lines of code, making it more readable and a lot easier to maintain. For my job, I have to write scripts in Bash all the time. I generally opt for Bash when I need to automate just a few lines of code, and using Python wouldn't add any additional value. For example, I had to write a short Bash script recently that mounted several disks one by one and compressed and archived the data on them. Over the next several videos, we'll look at the syntax needed to do some basic operations in Bash, like conditionals or loops. You'll see how it's comparable to Python's syntax, but not exactly the same. Still, it's similar enough that it will be much easier to understand now that you already know how to program in Python. By the end of this module, you should feel much more comfortable interacting with many system commands available on Linux and creating your own scripts in Bash and knowing when to choose Python or Bash for your scripts. Remember, if your palms are sweating and you're feeling nervous about the upcoming topics, we're here with you every step of the way. Whenever you get stuck, just go back and rewatch the videos, practice on your own, and engage with your fellow learners. The best way to learn is to stick with it. We've already used a bunch of Linux commands by now, so hopefully these commands aren't too foreign. You might remember that echo is a command used to print messages to the screen, cat is a command for showing contents of files, ls is a command to list contents of a directory, chmod is a command to change permissions of a file, and so on. As we called out before, a lot of these commands come from Unix. Back in the 70s, when designing how these programs should behave, the philosophy was that they should do one thing and do it very well, which means we have a lot of commands, each for doing a specific thing. We'll go through them quickly, but as usual, we'll provide a cheat sheet afterwards that you can use as a reference. You have plenty of time to review these commands and practice on your own. So, let's get started. To create a new directory, we use the makedir command. To change into that directory, we use the cd command. As you might notice, these commands don't print anything to the screen. This is normal and to be expected. A lot of the commands that we use don't print anything when they succeed. They only print something if they fail. To check that the cd command succeeded, we can use a command like pwd to print the current working directory. Okay, we have a directory, which is empty. We can copy files using the cp command. For example, we can copy the spider.txt file that we have in the parent directory. What are all those dots? These are shortcuts that we can use to refer to some special directories. The ..dot shortcut refers to the parent directory, the previous directory in the absolute path, while the dot shortcut refers to the current directory. So this command is copying the spider.txt file located in the previous directory to this directory. Does that connect the dots? We can also create an empty file using the touch command. So by now we have two files in our directory, the spider.txt file that we copied and the myfile.txt that we created using the touch command. Let's look at the contents of our directory using the ls-l command. Nice. We've now called the ls command using the -l command line argument. Remember, command line arguments let us change the behavior of commands, making them do what we want. Without any arguments, ls would just list the names of the files contained in the directory. By passing the -l, we get a lot of extra information distributed in a bunch of columns. Pop quiz time. What are these columns? The first column indicates the permissions of the file. The second column is the number of inodes that point to the file. The third and fourth columns indicate the owner and the group to which the file belongs. Then comes the size of the file, the date of last modification, and finally, the name. In our case, we have the file that we copied, which has 192 bytes, and another file that we created using the touch command, which has 0 bytes. Let's check out another ls command line argument by calling ls-la. The -a flag shows hidden files, which are the ones that start with a dot. In this case, the only ones are the shortcuts that we called out earlier, the dot shortcut for the current directory and the ..dot shortcut for the parent directory. The sizes of these directories are related to the amount of files in them. To rename or move a file, we use the mv command. To copy a file, we use the cp command, like we mentioned earlier. We've now renamed myfile.txt to emptyfile.txt and created a new copy of the spider.txt file. Each of these commands use the same format. The first parameter is the old file and the second parameter is the new file. Let's look at the contents of our directory now. We see that we now have two copies of our file with 192 bytes, and the empty file is now called emptyfile.txt. To delete these files, we can use the rm command. We can either go one by one, or we can delete them all together using the star. The star is a placeholder that gets swapped out by the names of all the files in our directory. So, our directory is once again empty. Now let's get rid of it. First, we need to change to the previous directory. We do that using cd ... Again, ... is the way we use to identify whatever was the previous directory. Alright, now we can delete the directory using rmdir. This command only works on empty directories, so it wouldn't work if we had left any files in it. This time, when calling the ls command, we passed the name of the directory that we wanted to list and got back an error because the directory didn't exist anymore. Did it ever really exist at all? It really makes you think. Anyway, that was a quick overview of some of the commands we have in Linux to operate with files and directories. There are tons of other commands to talk about, but not enough time to talk about them all. We'll mention some of them in the next few videos and put more info about them in the cheat sheet. Make sure to investigate and practice using them all on your own. Remember that reading the documentation for any given system command can help you learn more about what it does. On Unix-based systems, this documentation can usually be found in manual or man pages using the man command. Let's keep moving. Up next, we'll talk about a different aspect of the command line interaction: how to redirect I/O streams. See you there. So, now that we've covered a few basic Linux commands, let's talk more about what we can do with I/O streams in Bash. In an earlier video, we talked about the standard I/O streams. By default, the input is provided by the keyboard at the text terminal, and the output and error are shown on the screen. This is the case not only for our Python scripts, but for all system commands. We can change this default using the process called redirection. Redirection is a process of sending a stream to a different destination. This process is provided to us by the operating system and can be really useful when we want to store the output of a command in a file instead of just looking at it on a screen. To redirect the standard output of a program to a file, we use the greater than symbol. For example, take the following Python program, which just prints a single line of text using the print function. If we run this program without redirection, the text will be sent to the display using the stdout normally. But now, if we use the greater than character to redirect the output instead, something else happens entirely. When we run it this way, the stdout from stdoutexample.py script is redirected to a file called newfile.txt. If that file doesn't exist, it's created. Let's look at the contents of newfile.txt using the cat command. You see that? The output of our program ended up in the file that we wrote after the greater than symbol. Beware, just like we saw earlier with the W file mode used by the open function, each time we perform a redirection of stdout, the destination is overwritten. So, we need to be super careful when using this redirection that we're not overwriting a file with valuable contents. If we want to append the redirected standard out to a file, we can use the double greater than sign instead of a single greater than. Isn't that great? In a similar way, we can also redirect the standard input. Instead of using the keyboard to send data into a program, we can use the less than symbol to read the contents of a file. Let's try this out with a new version of the streams.py file that we saw in an earlier video. Okay, now let's redirect the contents of our new file to this script. Awesome. In this case, we don't see the input on the screen in the stdin portion. This is expected because the input was read from a file. So it only appears in the stdout portion where we see that it read one of the two lines. This is also expected because the input function only reads until it encounters a new line character. It can also be useful to redirect stderr to capture errors and diagnostic messages from a program. This can be done by using the character combination to greater than, similar to how we redirected stdout before. Let's execute our stream example again, this time redirecting the error output to a separate file. So this time, we don't see the error message on the screen. That's because we redirected it to the error file. Let's see if we can find any goodies in the contents of that file. Aha! There's our error. If you're wondering about the number 2, it represents the file descriptor of the stderr stream. In this context, you can think of a file descriptor as a kind of variable pointing to an I/O resource. In this case, the stderr stream. 0 and 1 are the file descriptors for stdin and stdout. Like we called out already, none of this is exclusive to Python. We can operate in the same way with all other commands. For example, we can create a file using the echo command and redirecting its output to the file that we want to create. Boom. And as usual, we can see the contents of our new file using our friend cat. Alright, So now we've seen how we can redirect input and output to files. How about redirecting between programs? That's coming up next in our next video. On top of the redirection to and from files that we saw in the last video, there's another powerful way to perform I/O stream redirection called piping. Using pipes, you can connect multiple scripts, commands, or other programs together into a data processing pipeline. Pipes connect the output of one program to the input of another. This means we can pass data between programs, taking the output of one and making it the input of the next. Pipes are represented by the pipe character. Using pipes is an extremely useful tool. It allows us to create new commands by combining the functionality of one command with the functionality of another without having to store the contents in an intermediate file. So let's work on our plumbing, shall we? Here's an example. Here, the output of the ls-l command is connected to the input of the less command, which is a terminal paging program. This example can be pretty useful when you want to look at the contents of a directory containing lots of files. The list of files generated by ls is piped to less, which displays them one page at a time. We can scroll up or down using the page up, page down, or arrow keys. And once we're done looking at the files, we can quit with Q. But it doesn't have to stop there. It's possible to connect a lot more than just two programs using pipes. We'll check this out using a more elaborate example. That's a complex command line. Let's go through it step by step. We're first using cat to get the contents of our spider.txt file. Those contents are then sent to a command called tr, which gets its name from the word translate. It takes the characters in the first parameter, in this case it's a space, and then transforms them into a character in the second parameter. In this case, it's a new line character. So basically what we're doing is putting each word in its own separate line. Hooray for organization. Next, we pass the result to the sort command through a pipe. This command sorts results alphabetically. The sorted results are then passed to the unique command, which displays each match once, and by using the -c flag, it prefixes each unique line with the number of times it occurred. This output is passed via pipe to the sort command once more, this time with the -nr flag, which sorts results numerically and in reverse order, from most to least hits. The output is finally passed to the head command, which prints the first 10 lines to stdout. Whoa, that's a lot to process. But when you break it down, it makes a lot of sense, right? The point isn't to memorize all these commands, but to know that we can pipe as many commands as we need to do exactly what we want. You can use your Python scripts in pipelines too. Python can read from standard input using the stdin file object provided by the sys module. This is a file object like the one we obtained using the open function. And, like your local library, this file object is already open for reading. Let's say we want to write a script that reads each line of the input and then prints the line with the first character in uppercase. To do this, we'll take advantage of the capitalized string method. It'll look something like this. In this script, we're iterating over the contents of the sys.stdin file. Remember that when we iterate a file object, we go through it line by line. For each of the lines of a file, we first use the strip method to remove the new line character at the end, then capitalize method to make the first character of the line uppercase, and then we print it out to standard output. Now, let's use a script to capitalize a file that we have in our computer called haiku.txt. Let's see the contents of it using cat. Shakespeare couldn't have said it better. Now, let's use a pipeline to capitalize our haiku by combining the output of the cat command with our capitalized script. The cat command sends the contents of the haiku.txt file to standard output, which we redirect to our script using a pipe. Our capitalized script uses the sys stdin_file object to iterate through each line of standard input, printing the capitalized version to standard output. It's truly poetic, isn't it? We should also call out that we don't need to use a pipe to get the contents of the haiku.txt file into standard input of our script. Instead, we use the redirection operator we saw in the last video, like this. As a rule, if you just need to get something from standard input into your script, using a redirection is enough. But if you want this to be part of a bigger pipeline of commands, you'll need to combine them with pipes. For example, if we only want to capitalize the lines that match a certain pattern, we could first call grep and then connect it with the pipe to our script. With a little practice, creating pipelines is a fast and powerful way to perform lots of system administration tasks. When a system command doesn't exist with the functionality that you need, you can write a Python script to fill in the gap and include it in your pipeline. Understanding how to redirect I/O streams can come in handy in many situations and when writing code too. We'll see plenty of more examples of this down the pipe. Get it? Pipe? Okay, sorry. Up next, we'll dive into the different ways we can send signals to the running processes on our computer. When dealing with the operating system, we usually have a bunch of different processes that we use to accomplish what we want. And like any well-oiled machine, we generally need these processes to communicate with each other. For example, we might have a program that starts a background process and wants it to terminate after a timeout. One way of communicating this is through the pipelines we learned about in the last video. Another way of communicating is through the use of signals. Signals are tokens delivered to running processes to indicate a desired action. Using signals, we can tell a program that we want it to pause or terminate. We can also cause it to reload its configuration or to close all open files. Knowing how to send these signals lets us interact with processes and have more control over how they behave. There are a bunch of different ways that we can send these signals. For example, let's execute the ping command in our terminal. The ping command is now running, sending ICMP packets to a machine over the network once per second. And it will keep running forever unless we interrupt it. To do that, we can use the Control-C combination. See how when we interrupt it, the program doesn't just end abruptly. First, it prints a summary of what it did and what the results were. It's very polite under these circumstances. What's happening behind the scenes is the process received a signal indicating that we wanted it to stop. When that signal is received, the process does whatever it needs to finish cleanly. The signal that Control-C sends is called SIGINT. It's just one of many signals that we can send. Another keyboard combination that we can use to send a signal is Control-Z. Let's try this one out. So, our ping is running once more. This time, we'll interrupt it with Control-Z. Uh-oh, this time the process didn't finish properly. We get a message saying that it stopped. What's going on? The signal that we sent is called SIG_stop. This signal causes the program to stop running without actually terminating. But don't worry, we can make it run again by executing FG. The FG command makes our program run once more. And it'll keep going until we interrupt it, either with Control-C, Control-Z, or some other signal. Let's stop it now with Control-C. By pressing Control-C this time, we've made the program finish cleanly. To send other signals, we can use a command called kill. Yikes. By default, kill will send a signal called SIGTERM that tells the program to terminate. Since kill is a separate program, we need to run it on a separate terminal. And we also need to know the process identifier, or PID, of the process that we want to send a signal to. To find out the PID that we want to send a signal to, we'll use the PS command, which lists the currently running processes. Depending on what options that we pass, it'll show different subsets of processes with different amounts of detail. For this example, we'll call PS AX, which lists all the running processes in the current computer. And then we'll use the grep command to only keep lines that contain the name of the process that we're looking for. Sound good? Okay, let's try this out. We'll run ping on one terminal and then find its PID and kill it from a second terminal. Cool. So our PS and grep commands found that the PID for the running ping command is 4619. We can now use this identifier to send the signal that we want using the kill command. We've now sent the sig term signal and the process was terminated. Hasta la vista, process. Notice how in this case we didn't get the nice summary at the end. The program just finished. As you might expect, there is more signals that we can send, and they might cause programs to react differently. Many long-running programs, for example, will reload their configuration from disk if we send them a signal. This way, we can let the program know that there's an important change in the configuration and it can get applied without the program having to stop to reread it. Programs that provide web services might also receive a signal to tell them that they should finish dealing with any currently open connections and then terminate cleanly once it's done. Understanding what these signals are and how to send them will let you interact with the processes on your system that you're in charge of and make them behave as you want. Coming up, a couple of readings to put all of this information in one place. We'll list all the system commands that we came across and some that we'll encounter later on. We'll also list other resources that you can use if you want to learn more. As we've said before, you don't need to memorize any of this. You'll get better by using them in our practice exercises and by experimenting on your own. To wrap this up, there'll be a quiz to let you practice your understanding of these concepts. The anticipation is killing me. We mentioned in earlier videos that Bash is the most commonly used shell on Linux. Bash is not only the interpreter that runs our commands, it's also a scripting language. We can use Bash to write simple scripts when we need to use a lot of commands. In the next few videos, we'll learn how to write these scripts and why they're useful. Let's start with an example of why you would even want to do this. In your job as an IT specialist, you sometimes need to debug a computer that's not behaving correctly. There are lots of commands that can tell you what's going on in there to help you with your debugging. For example, the ps command can list all the current running processes. The free command can show you the amount of free memory. The uptime command can tell you how long the computer has been on, and so on. Anytime you need to debug a computer, you can manually run these commands one by one, followed by as many commands as you can think of that might be helpful. But that already sounds tedious, just describing it. What if, instead, you can run a single command that can gather all of this information in just one shot? Well, I have some good news for you. We can do this by creating a bash script that contains all of the commands that we want to call, one after the other. Let's start with a simple version of a script like that. The script we're seeing here is calling three main commands: uptime, free, and who, which lists the users currently logged into the computer. It uses the echo command to print some other information and to make the output a bit more readable by leaving empty lines between the commands. We're also calling the date command to print the current date. To call this command, we're using a special notation by putting the command inside $ parentheses. This indicates that the output of the command should be passed to the echo command and be printed to the screen. Now, let's execute our bash script and see what happens. Yay! Our script is working as expected. The starting and finishing times are the same because there are so few operations we're doing that it takes the computer less than a second to complete them. Not too shabby. Once we add more operations to gather other information, it might take a bit longer. So that's a simple script. We can keep adding more and more commands to it to make our information gathering command get everything that's relevant for debugging. Now see that as the script is written right now, there's one command per line. That's a common practice, but it's not the only way. We could also write the commands on the same line using semicolons to separate them. Let's see what that looks like. And now let's execute it to check that it still works the same as before. Yep, still working as expected. Alright, that was our first bash script. That wasn't too bad, was it? Believe it or not, you've now learned how to write scripts in 2 different programming languages, Python and Bash. Pretty cool, huh? We're just getting started. There's a lot more coming up in the next few videos. Like we said in an earlier video, Bash is a fully powered scripting language, not just a way of executing commands one after the other. We can assign variables, do conditional operations, execute loops, define functions, and so much more. So much that we'll only get to cover the very basics in these next few videos. Let's start with variables. Much like Python, Bash lets us use variables to store and retrieve values. In an earlier video, we looked at environment variables. These are variables that are set in the environment in which a command is executing. We mentioned that we set these variables using the equals sign. And when we want to access the value of a variable in Bash, we need to prefix the name of the variable with the $sign. On top of the predefined environment variables, we can also define our own variables for our scripts. To do that, we just assign a value to the name of the variable that we want to define. Nice. But heads up, there can be no spaces between the name of the variable and the equal sign, or between the equal sign and the value. If we try to define a variable and leave a space at one side or the other, the shell will complain that it can't find the command with the name that we're assigning. My bad. Also, remember that any variable that you define in your script or in the command line is local to the environment where you define it. If you want commands from that environment to also see the variable, you need to export them using the export keyword. Okay, let's now modify our script to gather info and add a variable to it. We'll use it to make our script look nicer by adding lines in between each of the commands. To do this, we'll define a variable called line, and we'll put a bunch of dashes in it. And now, instead of leaving empty lines, we'll print this variable to separate our commands. And now, let's try executing the modified script. Perfect. There you have it. We've set and used a variable in our Bash script. Let's move on to another interesting feature available in Bash called globs. Globs are characters that allow us to create lists of files. The star and question mark are the most common globs. Besides being extremely fun to say, globs, using these globs lets us create sequences of file names that we can use as parameters to the commands we call in our scripts. You've probably come across them before, but let's do a quick recap of how we can use them. In Bash, using a star in the command line will match all file names that follow the format that we specify. Let's check out a few examples. We can see that when we write star.py, the shell turns it into a list containing all the file names that end with py in the current directory. We can also put the star at the end of an expression to get the list of all files that start with a certain prefix. In this case, we get all the files in the current directory that start with the letter C. We can also use a star with no prefix or suffix, which would match all the files in the current directory. Alternatively, the question mark symbol can be used to match exactly one character instead of any amount of characters, and we can repeat it as many times as we need. For example, we can get the Python files with 5 characters in their name by using the 5 question marks together. Using globs like this lets us create lists of files that we might operate on, like calling other commands and passing this list. If you want to use this functionality in Python, it's available through the glob module. That might sound like something an alien might say, but it's actually pretty powerful. And of course, there's a lot more we can do with bash scripting. Coming up in the next video, we'll talk about conditional execution. One of the main concepts of programming is being able to branch the execution according to a condition. In other words, making our program behave in different ways depending on one or more values. In Python, we use the if block, and the condition is an expression that has to evaluate to true or false. In bash scripting, the condition used is based on the exit status of commands. Do you remember what we discussed earlier about the exit status of commands? We mentioned that we check the exit status of a command using the $question mark. And we called out that in bash scripting, an exit value of 0 means success. This logic is used by the if operator in bash. To create a conditional expression, we're going to call a command, and if the exit status of that command is 0, then the condition will be considered true. Say we wanted to verify that the /etc/host file contains an entry for 127.0.0.1, which it should. Knowing that grep will return an exit status of 0 when it finds at least one match, and different than 0 if it doesn't find a match, we can use it to do this verification. Check out this script. Let's look at the syntax of the if block. We start with the if keyword followed by the grep command that we'll use to check for success. At the end of the command, we have a semicolon followed by the word then. After that comes the body of the conditional. Make sense? We're using indentation like in Python. This is a good style choice and it makes the code more readable, but it's not mandatory in bash. It's possible to write this in one line, and sometimes we might do that when the amount of code is small enough. In general though, it's nice to have commands in separate lines and use indentation to clearly show the body of the conditional. We also have an else block for when the command doesn't finish successfully. And finally, our conditional block finishes using the fi keyword. You can see how some things are the same as in Python. It uses the if and else keywords. It checks the condition and branches the execution according to the value of the condition. But other things are different. We need to write semicolon then before we can start the body, and we need to end the block with fi. Paying attention to these similarities and differences will make it easier for you to get acquainted with new programming languages. Okay, let's run our script and see what it does. Here we go. The first line in the output is the one generated by our grep command, because by default, grep prints the lines that match the expression that we give it. The second line in the output is the one that was generated by our script. So, in this case, the grep command called by our script found the line in the file and exited with a value of 0. So our script said that everything was okay. If grep hadn't found that line, it would have exited with a value different than 0, and we would have received a different message. There's plenty of other conditions that we might want to check in our scripts. If a file exists, if 2 strings are equal, if a number is less than another number, and so on. To help us with evaluating these conditions, there's a command called test. Test is a command that evaluates the conditions received and exits with 0 when they're true and with 1 when they're false. Let's check out an example. In this case, it's short enough that we can write everything in one line. We're using the -n option for the test command, which checks if a string variable is empty or not. In this case, path isn't empty, so we get the message. Using the test command like this is so common there's another way of writing it, which looks more like other programming languages. It's something like this. In this case, the command we're calling is the opening square bracket. This is an alias to the test command. But to call it successfully, we also need to include a closing square bracket. When using this syntax, remember that there needs to be a space before the closing bracket. There's plenty of other things that we can check with test, but we won't cover them in these videos. We'll include some of them in the upcoming cheat sheet, and you can also see all of them by looking at the manual page for test. So, by now, you have a rough idea of what a bash script looks like. You're doing really good. And remember, you can always review the contents if something isn't clear. There's a lot of topics that we haven't covered yet, like working with loops or managing command line arguments. But before we jump into that, let's do a quick quiz. Welcome back. Let's take a moment to quickly recap everything you've learned so far in this module. We started by looking at some of the most common Linux commands. You learned about redirecting streams, pipes and pipelines, and signaling processes. Then you got your first taste of the bash programming language, including how to create a script, use variables and globs, and perform conditional execution. That's a lot of new interesting concepts that will help you get the most out of the systems that you work with. But we aren't done yet. Let's dive into some more advanced bash concepts before we wrap up this module. Are you ready? Good, let's do it. Bash provides similar looping structures to Python. We can iterate while a condition is true using a while loop and iterate over a list of elements using a for loop. Although, of course, the syntax for these loops is slightly different. As a quick reminder, loops are what makes the computer do repetitive tasks for us. Anything from working with a bunch of numbers to processing the contents of a file line by line. Our computer doesn't care how many times we ask it to do what we want. It'll keep doing them until it's done. No coffee breaks. So sad. Let's check out a simple while loop in bash. In this script, we're using the variable n to print messages, counting from 1 to 5. The condition for the while loop uses the same format as the condition for an if block. In this example, we check if the variable n is less than or equal to 5 using the -le operator. The loop itself starts with the do keyword and finishes with the done keyword. To increment the value of the variable n, we're using a bash construct of double parentheses that lets us do arithmetic operations with our variables. It seems complicated, but when you take a step back, it all comes together. Let's execute this and see what happens. Okay, so that works. But what about making our loop a bit more interesting? When using while loops in bash scripts, it's common to have a loop that retries a command a number of times until it succeeds. This is really useful with commands that use network connections or that access resources that might be locked. These commands can fail for external reasons, and they are likely to succeed after a retry or two. To simulate a command that sometimes succeeds or sometimes fails, we have a small Python script that will return an exit value picked at random from a range that we give it. Do you see what the script is doing? It uses random randint to generate a value between 0 and 3. Then it prints the selected value and exits with it. Let's check this script out. Cool, so we see that we get a value in the 0 to 3 range. Which value we get will depend on each call. That's okay. We want to simulate a command that sometimes fails and sometimes succeeds. Now, let's have a look at our bash script that'll retry the command. This script is a bit more complex than the earlier one, but not by much. One interesting difference is that we're getting the value of a command line argument using the $1. This is what we use in bash to access the first command line argument. In Python, we get the same information using sysargv1. So, we store the parameter in the variable called command, and then we execute the while loop until either the command succeeds or the end variable reaches a value of 5. In other words, if the received command fails, we'll retry up to 5 times. In the body of the while loop, we first sleep a few seconds, then increment the variable and print the number of retry attempts. So why do we call the sleep command? This is no time for rest. The idea here is that if the command we're calling is failing due to CPU usage, network, or resource exhaustion, it might make sense to wait a bit before trying again. So the more we try, the more we wait. We need to let our computer catch a breather and recover from whatever is making our command fail. In our simulation, the command fails randomly, but this retry script works with any other commands that could fail for a wide range of reasons. To try this out, we'll need to call our retry script with the random exit command as a parameter, like this. We can see how our script keeps executing until the command that we passed returns 0, which is exactly what we wanted, 0 problems. This last example is a real-world use case for while loops in Bash and includes a few more advanced topics. So it can definitely feel complex. But don't let that stop you. Rewatch this video as many times as it takes and practice the scripts that we covered. Once you're ready, you can meet me over in the next video where we'll look at for loops in Bash. Both in Python and Bash, for loops are used to iterate over a sequence of elements. You might remember that the key to for loops is that they let us perform an operation on each of the elements in a sequence. In Python, the sequences are data structures like a list, a tuple, or a string. In Bash, we construct these sequences just by listing the elements with spaces in between. Let's check this out using a very simple example. In this case, we're iterating over 3 different elements that have the names of fruits. See how the for loop uses the same do-done structure that the while loop used before? Now, let's execute this script and check that it does what we expect it to do. Alright, that seems simple enough, but it's low-hanging fruit. Tasty for sure, but not that useful. We called out in an earlier video that in Bash, we can use globs like star and question mark to create lists of files. These lists are separated by spaces, and so we can use them in our loops to iterate over a list of files that match a criteria, like all the files that end in .pdf, all the files that start with img, or whatever it is that we need. Let's use a practical example to see this in action. Imagine that you're migrating your company's website from one web server software to another. Your web content is stored in a bunch of files that all end in uppercase HTML. And the new software requires that they all end in lowercase HTML. Disaster. You can manually rename them one by one using the mv command, but that could get really old really fast. You'd likely end up making mistakes after the first few commands. Instead, you could do the same thing with a short Bash script. First, let's check out our files. Okay. Looks like we have 5 files that we need to rename. So how can we extract the part before the extension? There's a command called basename that can help us with that. This command takes a file name and an extension and then returns the name without the extension. Just like that, we're ready to write our script and rename the files. We'll start, as usual, by including the bash shebang line. Our script will iterate with a for loop through all the files that end with .htm. So, now, for each file, we want to call basename to keep the part of the file that we care about. We'll store that in a variable called name. Easy enough. And now, we'll use $ parentheses to call the command and keep the output. We're surrounding our file variable with double quotes to allow the command to work even if the file has spaces in its name. This is a good practice in bash scripts when dealing with file names or any variables that could include spaces. Now, we'll call the mv command with the old and new names. In this case, we use double quotes for both parameters. Again, we want to make sure that it works correctly for file names with spaces. And that's all that our loop needs to do. We'll finish our loop with the done keyword. And we're done. Almost. We still need to run our script to see if it does what it should. Now, let me share a trick with you that might save you a few headaches. Whenever you're going to run a script like this that modifies the files in your file system, it's a really good idea to first run it without actually modifying the file system. This will catch any possible bugs that the script might have. So, instead of just running it as it is right now, we'll add an echo in front of the mv command. This means that instead of actually renaming, our script will print the renaming that it plans to do. Now, let's save this script, make it executable, and run it. Excellent. Our script printed the actions that it would take, and it looks like it's going to do the right thing. So, let's remove the echo and make it actually rename the files. This time, it didn't print anything. That's expected, because these commands don't print anything when they succeed. Let's check that our rename worked by listing the contents of our directory. Yes, we managed to rename all of our files successfully, and they all lived happily ever after. Hopefully by now, you're starting to see how you can benefit from using bash scripts when dealing with files and system commands, especially to complement your Python scripts. Up next, we'll use all this bash scripting knowledge to solve an interesting system administration challenge. Stay tuned. Over the past few videos, we've learned a lot about how to do things in the Linux command line and in bash scripts. We'll now look at a couple interesting applications for all these bash scripting powers that we just learned to put all this new knowledge into action. Let's go back to our old friend, the system log file, located in var log syslog. The system log file contains a trove of information about what's going on in the system, so it's really important to learn how to get information out of it. Let's use the tail command to look at the last 10 lines in the file right now. The log lines we see follow a similar pattern. First, they include the date and time of when the entry was added to the file, then the name of the computer, then the name and PID of the process that triggered the event, and finally, the actual event that's being logged. Take a second and look at those lines. Say that we had a computer that was under significant load, but we didn't know why. And to find out, we wanted to check what events are being logged the most to our syslog. To do that, we need to extract the part of the line that has the actual event without the date and time. We could use a command called cut to help us with that. This command lets us take only bits of each line using a field delimiter. In this example, we can split the line using spaces. That would look something like this. In our example, we're passing -d space to cut to tell it that we want to use a space as a delimiter, and -f5- to tell it that we want to print the field number 5 and everything that comes after it. With that, we remove the date and the name of the computer, keeping only the process and the event message. Snip, snip. Now that we have the information that we care about, we can pipe this to the same pipeline of commands that we saw in an earlier video to find out the lines that are repeated the most. Like this. As you can see, we've chained together a bunch of commands so that we get the most repetitive lines in our syslog file. There are more files in var log that we might be interested in. So we can use a for loop to iterate over each of the log files in var log and get the most repeated lines in each of them. I know what you're thinking. This sounds like it's getting a little bit too complex for a one-line chain of commands. We're better off putting this into a bash script, something like this. In this script, we process all files in var log that end in log. We then print the name of the file that we're processing and then use the same group of commands as before to print the top 5 lines in each file. Ready? Let's execute it and see this in action. Nice. Our script shows us the most common lines on each file in var log. There are a lot of files in there. And with that, we wrap up our introduction to bash scripting. Amazing work. Now that you have scripting skills in both Python and bash, you might be wondering when to use one versus the other. Well, we'll talk about that in our next video. See you there. As you can probably tell by now, there's a lot of interesting things that we can do with the system commands. We've come across a bunch of different commands that can help us operate with files and processes and get more information about the computer, process the contents of files, and all sorts of other things. By using bash scripts, we can very quickly turn a command that operates on just one file into an automated script that handles 1,000 files. Pretty powerful, right? As we saw with our log file examples, there's a bunch of terminal commands that provide text processing functionality. Plenty of them also support regular expressions, allowing us to do some very advanced processing of the data in our files. When these commands are linked together in a data processing pipeline, they can become a powerful tool for processing text data. They can give us the information we're looking for quickly without the need to write a full script. But you know what they say about great power. We need to be careful not to abuse this because it can quickly become unreadable. Take a look at this example. Yuck. This command line is using some stuff we saw and some other stuff that we didn't look into, like how to do indexing on bash strings to turn the first letter of each word into uppercase. We can probably agree that this command line is pretty unreadable. If there happened to be a bug in it, it would be really hard to figure out how to fix it. When a bash command line starts becoming this complex, it's a better idea to write a Python script that handles the data in a more readable and testable way. A simple script could look like this one. In this example, we take each line of standard input, remove the white space, and split it into separate words. Then, we use a list comprehension to capitalize each of the words and end up joining them back with spaces and printing the output. Once we have the script, we can execute it as part of a pipeline like this. So, it's a good idea to choose bash when we're operating with files and system commands, as long as what we're doing is simple enough that the script is self-explanatory. As soon as it becomes hard to understand what the script is doing, it's better to write it in a more general scripting language like Python. Bash scripts aren't as flexible or robust as having an entire Python language available, with its many functions to operate on strings, lists, and dictionaries. There's another gotcha when it comes to bash and Linux commands, and it's something that we've said before. Their availability depends on the platform that we're using. Some commands might not be present on certain operating systems. Writing a bash script can get the job done very quickly on a Linux machine, but it won't work on a Windows machine. There, we'll need to write the same script in PowerShell. So, if the task that you're trying to accomplish is limited to the current server or a fleet of servers, all running the same operating system, a simple bash script can get the job done. But if your code is complex or you need it to work across platforms, you might be better off using the Python standard library or other external modules that provide the same functionality. Last thing, there are lots of situations where either a Bash script or a Python script might solve the problem just fine. In those cases, you can choose whichever one you feel more comfortable with. Pick your poison. Hopefully, this is all starting to make sense. Whether you choose to write a Bash script or Python, both of these skills are going to serve you well in an IT environment. Congrats on making it all the way here. We're almost to the end of the course. Please accept this virtual high five. By now, you're probably seeing why Linux happens to be my favorite OS. As I mentioned way back in the first module, Linux is the primary OS that I use in my day-to-day job as a system administrator. Even though I grew up using Windows computers for personal use, Linux opened up a whole world of customization and configuration that I was missing on Windows. I found the challenge interesting, and I hope you do too. In this module, we deep dived into the many benefits that Linux command line has to offer. We learned about redirecting streams to both files and processes. We learned about sending signals to our processes to stop them or let them continue. We also learned about creating Bash scripts, a whole new programming language. We looked into how we can use variables, conditionals, and loops in our Bash scripts to combine system commands and make them do what we want. And finally, we looked at when to choose Bash or Python for our scripts. Being able to write simple Bash scripts allows system administrators to quickly automate manual tasks. Tasks like renaming files, retrying commands, finding information in log files, and so on. Once you're familiar with writing scripts like these, you can get tasks done promptly and then use your time to focus on things that require more of your expertise. I love to be able to get creative and think big in my job, and automation frees me up to do that. There are lots of machines in the lab where I work at Google that require configuration, and it would take forever for me and my team to configure each machine one at a time. By automating some of these tasks, I can get the job done quickly and have time to work on new and more interesting projects. In the graded assessment coming up, you have the opportunity to write both Bash and Python scripts to solve a real-world problem. Remember, you can use all the materials that we've covered up until now to help you get this done. Good luck. I know you got this.